Imagine being asked to sentence your great-grandchildren's great-grandchildren to a life they never agreed to live. Born inside a sealed metal world that offers no exit, propelled through radiation-soaked darkness toward a star, none of them will ever remember choosing. That is what a generation ship actually is, not the luminous arc of science fiction, not a noble colony vessel drifting gracefully between suns. A generation ship is a closed civilization, locked inside a container, expected to function without interruption for longer than the Roman Empire endured, with nothing flowing in from outside and no passage back to the world that built it. The most ambitious, sealed ecosystem humanity has ever assembled began deteriorating within months and barely held together for 2 years before requiring intervention from outside. A generation ship would need to sustain a comparable system not for 2 years but for 2 centuries. Hors four, hors ten. The engineering is not the most frightening part. Keeping human beings from coming apart is, and the real numbers, when you examine them honestly, are considerably worse than most people are prepared for. If you find yourself drawn to journeys that fundamentally alter how you understand humanity's place in the cosmos, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach people who are looking for exactly this kind of story. Now settle in, get yourself comfortable, and clear your mind of whatever else is pressing. Let's begin. The closest star to our sun has a way of defeating the imagination, not through menace, through distance alone. Proxima Centauri lies 4.25 light-years from Earth. That figure sounds almost reasonable until you translate a light-year into something the human mind can grip. 1 light-year equals approximately 5.88 trillion miles. Multiply that by 4.25 and you arrive at a number that ceases to carry meaning. Roughly 25 trillion miles of nothing, vacuum, radiation, and a cold so absolute that the background temperature of interstellar space hovers only a few degrees above the threshold, where all molecular movement stops entirely. NASA's Voyager 1 probe, which left Earth in 1977, remains the most distant human-made object ever launched. It has been traveling for nearly 5 decades, at approximately 38,000 miles per hour. At that velocity, Voyager 1 would require more than 73,000 years to reach Proxima Centauri. Let that settle for a moment. 73,000 years. When Voyager launched, the internet had not yet been conceived. 73,000 years ago, anatomically modern humans had not yet pushed into Europe, and Neanderthals still possessed the continent entirely to themselves. The full sweep of recorded human civilization, every empire, every cathedral, every revolution, every satellite, every smartphone, occupies roughly the last 5,000 years. Voyager would need to travel for 14 times the entire length of recorded history, simply to arrive at the nearest star. And Proxima Centauri is not even a particularly interesting destination. It is merely the closest one. This is the barrier that the generation ship concept was created to cross. Not a wall of political will or engineering ambition, a wall of time. Human beings live approximately 70 to 80 years on average. Even the most optimistic projections for extending human longevity rarely push that figure past 150. Interstellar distances, under any propulsion system that respects known physics, demand travel times measured in centuries or millennia. The gap between one human lifetime and the duration of an interstellar crossing is not a technical inconvenience waiting to be engineered away. It is a categorical mismatch. No single crew can survive the transit. Not because the vessel would fail them, because they would die of old age long before it ended. Faster travel would resolve this. But faster travel does not negotiate with physics. To reach Proxima Centauri within a single human lifespan, a spacecraft would need to move at a meaningful fraction of the speed of light. At 10% of light speed, approximately 67 million miles per hour, the journey would compress to around 42 years, which is within reach of a human lifetime. But accelerating even a modestly sized vessel to that velocity demands energy on a scale that eclipses anything humanity has ever produced. The kinetic energy required exceeds the combined yield of every nuclear weapon ever constructed by multiple orders of magnitude. And that accounts only for acceleration. Decelerating at the far end requires the same energy expenditure all over again. The fuel problem alone is catastrophic. Conventional chemical rockets cannot approach these velocities regardless of how much propellant they carry, because the mass of the fuel itself demands additional fuel to move it. This creates a diminishing return spiral that collapses into absurdity long before interstellar speeds are reached. Scaling any such system to carry human beings multiplies the energy requirements by factors so large the endeavor passes from ambitious into the realm of the fantastical. The physics functions reasonably for postage stamp-sized probes. It does not function for people. 3 options remain for moving human beings between stars. The first is cryogenic suspension, freezing the crew and reviving them upon arrival. The difficulty is that reliable, reversible human cryopreservation does not exist. No human being has ever been frozen solid and successfully brought back to life. Vitrification techniques show measured promise for preserving isolated organs, but scaling that process to an entire living body and achieving safe revival after decades or centuries remains firmly in the domain of speculation. This is not a technology nearing readiness. It is a technology whose most basic feasibility has not yet been demonstrated at any level. The second is relativistic travel, pushing the vessel fast enough that time dilation becomes significant. A crew moving at 90% of light speed would experience the crossing to Proxima Centauri in under 2 years of subjective time, but reaching 90% of light speed reintroduces the energy problem, amplified by relativistic mass increase. The closer a physical object approaches the speed of light, the more energy each additional increment demands, with the requirement climbing asymptotically toward infinity at the limit. Relativistic travel is permitted by the equations of physics. It is forbidden by any realistic energy budget. The third option is the one that presents itself as the most reasonable precisely because it demands no new physics, no speculative technology, and no impossible energy. Rather than shortening the journey, you accept its duration and engineer around it. You construct a vessel large enough to sustain a human population indefinitely. The crew lives, works, reproduces, raises children, ages, and dies aboard. Their children do the same. Generation after generation inhabits the ship in transit until, perhaps centuries later, descendants of those original crew members arrive at the target star. This is a generation ship, and on the surface, its logic is almost seductive. You are not breaking any laws of nature. You are not fabricating suspended animation from nothing. You are not producing energy equivalent to a small star. You are simply building something large enough to support life for a very long time and populating it with people willing to begin a journey they will never finish. The problem of distance becomes a problem of patience. The problem of speed becomes a problem of sustainability. Instead of fighting time, you surrender to it completely. You let the centuries accumulate while the ship moves at whatever velocity current or near-future propulsion can achieve. At 1% of light speed, roughly 6.7 million miles per hour, the journey to Proxima Centauri would take approximately 425 years. About 17 human generations at 25 years per generation. Long, undeniably, but not incomprehensible. Civilizations have persisted longer. Religions have endured longer. Family lineages have continued longer. The ancient Egyptians maintained a coherent civilization for more than 3,000 years. The Catholic Church has operated continuously for nearly 2 millennia. If human institutions can hold together for centuries on a planet with every advantage of open air and natural resources and contact with neighboring cultures, why could they not hold together aboard a well-provisioned ship? This reasoning sounds airtight. It is precisely why the generation ship concept has returned again and again in the thinking of scientists, engineers, and writers for over a century. The idea first appeared in recognizable form in Robert Goddard's private notes from 1918. It was explored in fiction by Don Wilcox in 1940 and given rigorous technical treatment by researchers at the British Interplanetary Society through the 1980s and 1990s. The concept persists because it appears to transform the most overwhelming problem in space exploration into a question of scale. Build the ship large enough, Supply it thoroughly enough, populate it thoughtfully enough, and the stars become accessible. But this is precisely where the seduction becomes a trap. The moment you accept the generation ship concept, you have not simplified the problem. You have traded one impossible challenge for a different, impossible challenge that merely looks more approachable from a distance. Consider what a generation ship genuinely requires. It is not an oversized spacecraft with additional living quarters. It is a completely closed, self-sustaining world that must recycle every molecule of breathable air, every drop of consumable water, every gram of nutritional matter, and every unit of biological waste without meaningful loss for centuries. Nothing can be imported after departure. Nothing can be restocked on the way. Every atom of oxygen the 15th generation breathes must have been sealed inside the hull on launch day. Every calorie the 10th generation consumes must trace its origins back to agricultural systems established before their great-great-great-great-great-great-grandparents were conceived. On Earth, ecological recycling is managed by a biosphere that required billions of years to evolve, spans the entire surface of the planet, and involves trillions of organisms interacting across thousands of interconnected cycles. When one part of this system fluctuates, others compensate. Forests absorb excess carbon dioxide, oceans moderate temperature swings. The system is not engineered. It grew. It is imprecise, redundant, and sprawling. And those very qualities are what make it resilient. A generation ship must replicate the essential functions of this planetary biosphere inside a sealed container. It must produce food, regenerate breathable air, purify water, decompose waste, and hold atmospheric chemistry within the narrow band compatible with human survival using artificial systems that cannot depend on planetary-scale buffers. If oxygen generation underperforms by 2% across a decade, the cumulative deficit becomes a crisis. If a crop pathogen eliminates one staple food source, the nutritional architecture of the entire population shifts overnight. If a microbial imbalance disrupts the waste decomposition cycle, toxic compounds begin concentrating in the air and water with no external reservoir capable of absorbing them. The most serious attempt to construct a closed ecological system on Earth was Biosphere 2, a 3.14-acre glass enclosure built in the Arizona desert that sealed 8 crew members inside from September 1991, September 1993. Biosphere 2 contains 7 distinct biome areas, including a miniature rainforest, an ocean basin, a savanna, a wetland, and a working agricultural zone. It was designed to be entirely self-sustaining, cycling all air, water, and food without external input. It began failing within months. Oxygen levels dropped from the normal 21% to approximately 14% conditions, equivalent to standing at roughly 14,000 feet of elevation. The cause was not a dramatic mechanical breakdown. Microbes in the soil were consuming oxygen faster than the plants could replace it, while excess carbon dioxide was reacting with exposed concrete in the structure, locking carbon and oxygen alike into calcium carbonate and removing them from the active cycle. The crew experienced persistent fatigue, cognitive impairment, and difficulty sustaining physical work. Crop yields fell below projections, leaving the inhabitants chronically underfed. 19 of 25 vertebrate species went extinct within the enclosure. Every pollinating insect died. Cockroaches and certain ant species flourished. The system never reached equilibrium. It lurched between imbalances, each attempted correction revealing new instabilities. Eventually, outside air had to be pumped in to prevent the oxygen deficit from reaching lethal levels. That single intervention effectively ended the experiment's validity as a closed system. The most sophisticated sealed biosphere humanity has ever constructed could not sustain 8 people for 2 full years without external rescue. A generation ship would need to run a comparable system, almost certainly far more complex, to support hundreds or thousands of people, not for 2 years, but for 2 centuries, or 4. And unlike Biosphere 2, there would be no emergency air supply waiting on the other side of the glass, no technicians watching through the windows, no Earth within reach. There would be nothing outside the hull but interstellar vacuum, extending for trillions of miles in every direction. This is the first fracture in the beautiful logic of the generation ship. The concept assumes that a closed ecological life support system can be engineered to operate reliably enough across centuries. No such system has ever been demonstrated at any scale for any duration remotely approaching what a generation ship would require. The longest continuously inhabited habitat in space is the International Space Station, occupied without interruption since November 2000. But the ISS is not a closed system in any meaningful sense. It receives regular resupply missions delivering food, water, spare parts, and equipment. Its atmosphere is regularly supplemented from pressurized tanks carried up from the surface. Its waste is ejected or returned to Earth. The ISS survives because it maintains a permanent lifeline to the ground. Sever that lifeline and the station becomes uninhabitable within weeks. But the ecological challenge is only the entrance to the labyrinth. Beyond it waits a cascade of compounding burdens that most generation ship proposals mention only briefly, if they mention them at all. A generation ship is not a spacecraft conducting a very long mission. It is a civilization. And the difference between those two things matters more than almost any engineering specification in any proposal ever written. A spacecraft has a crew. A civilization has a population. A crew follows orders, maintains discipline through shared training and professional hierarchy, and was selected for technical competence and psychological resilience. A population contains children who volunteered for nothing, teenagers who resist authority, adults who hold contradictory views on governance, and individuals whose personal ambitions conflict directly with collective survival requirements. You can screen a crew for cooperation. You cannot screen a population for cooperation across centuries of descendants, because those descendants do not exist yet when the screening occurs. The moment you accept that a generation ship will carry multiple generations, you accept that the majority of people aboard at any given time will not have chosen to be there. The founding generation volunteers. Their children are born into the mission, their grandchildren inherit it. By the 5th or 6th generation, no one alive aboard has any personal memory of Earth, any personal relationship with the original planners, or any personal connection to the target star. They were born on the ship. They will die on the ship. The mission is not their dream, it is their circumstance. They are, in the most literal sense that phrase can carry, living out a sentence imposed by ancestors they never met, locked inside a world they cannot exit, traveling toward a place that holds no felt meaning beyond inherited doctrine. This raises a question that no amount of engineering can answer. What compels Generation 9 to sustain a mission that Generation 1 began? On Earth, institutions persist across centuries, through a combination of cultural momentum, legal infrastructure, economic incentive, and the fundamental fact that people can leave if they wish to. A nation endures partly because its citizens choose to remain, and partly because neighboring nations offer alternatives. Aboard a generation ship, no alternative exists. There is no neighboring country. There is no immigration. There is only the vessel, the mission, and the void that surrounds both without limit. This is not stability, it is captivity. And captive populations throughout the entire record of human history have demonstrated a consistent and predictable tendency toward either rebellion or despair. The ethical dimension of this captivity is unlike anything human philosophy has previously been asked to confront. Every generation ship proposal implicitly assumes that one generation of human beings holds the moral authority to permanently shape the lives of every generation born after them aboard that vessel. The founders consent freely and with full information. Their children cannot consent in the same way. Their grandchildren cannot consent at all. And the consent of every subsequent generation is not merely uninformed, it is structurally impossible, because those people do not exist at the moment the decision is made. On Earth, societies routinely make commitments that bind future generations. Constitutions are drafted, debt is accumulated, environments are damaged, infrastructure is built. But in every terrestrial instance, future generations retain the capacity to alter, reverse, or walk away from what their predecessors decided. Constitutions can be amended, infrastructure can be demolished, environmental damage can be at least partially undone. The essential freedom of future generations to choose differently is preserved even when present generations make sweeping decisions, because the world remains open and alternatives remain physically accessible. A generation ship eliminates that freedom entirely. The descendants cannot revisit the decision to launch because the launch is irreversible. They cannot pursue an alternative path because no alternative path exists. They cannot leave the community because there is nowhere to go. Their reproductive choices may be constrained by population management requirements. Their professional options may be dictated by whatever labor the ship needs in their generation. Their daily lives may be governed by resource allocation schedules that existed before their parents were born. They are living out, in the most complete way, a life sentence handed down by people who believed the mission justified the imposition. No ethical tradition in the Western philosophical canon comfortably accommodates this degree of binding one generation to the choices of another. Utilitarian reasoning might defend the mission if the long-run benefit of establishing a human presence at another star outweighs the hardship imposed on intermediate generations. But this calculation requires assigning numerical weight to the well-being of people who have not yet been born, and comparing it against the concrete suffering of people who exist right now. A comparison utilitarian philosophy has never satisfactorily resolved. Deontological ethics, which center the inherent rights of individuals, would struggle to justify a project that permanently removes autonomy from people who were never asked. Virtue ethics might frame the mission as an expression of extraordinary human courage, but the courage belongs to the generation that decided to launch, while the sacrifice belongs to every generation that follows. The generation ship forces a confrontation with a question that terrestrial existence has had the luxury of deferring. What do the living owe the unborn? And, more unsettling still, what are the living permitted to impose upon the unborn? On Earth, this question is softened by the openness of the world. Future generations will inherit whatever environmental damage we cause, but they will also inherit the accumulated knowledge, rebuilt institutions, and the freedom to change course. Aboard a generation ship, future generations inherit a sealed world with fixed boundaries, fixed resources, and a fixed heading. They inherit constraint without freedom, obligation without choice, a mission without the consent that would make it bearable. Some theorists have proposed that the ethical problem dissolves if the ship is designed to be comfortable enough that its inhabitants would not want to leave even if they could. The structure of this argument deserves careful attention. It is essentially the argument that a cage becomes acceptable if the cage is pleasant enough that material comfort substitutes for the freedom to choose one's own direction. History consistently suggests otherwise. Gilded cages produce their own particular forms of resentment. The knowledge that departure is impossible transforms even comfort into confinement. Others have suggested that the mission itself provides sufficient meaning to offset the loss of individual freedom, that being part of humanity's most ambitious journey compensates for the absence of ordinary choices. But meaning cannot be imposed from outside a person. It must be felt from within. And the seventh generation, born into a world they never selected, heading toward a destination they have never seen, may not experience the voyage as an adventure at all. They may experience it as an inheritance they never requested, a burden placed upon them by people who are long dead and beyond any accountability whatsoever. Set aside the social dynamics for a moment. Set aside the psychology, the governance, the intergenerational resentment. Focus only on the physical container itself. The ship must be engineered to a standard that has no precedent in the entire history of human construction. Every structural component, every hull section, every seal, every pipe, every wire, every pump, every valve, every circuit must function reliably across centuries, not with scheduled maintenance by the original manufacturer, not with replacement components ordered from a global supply chain, but with whatever the ship carries on departure day, and whatever the crew can fabricate aboard using equipment that is itself aging. Modern naval vessels, among the most durable machines humanity assembles, have operational lifespans of 30 to 50 years. with continuous access to specialized dry dock facilities and planetary-scale supply networks. An aircraft carrier requires thousands of highly skilled workers at dedicated shipyards for periodic overhauls. A generation ship would need to operate for 10 to 20 times the lifespan of an aircraft carrier without ever visiting a repair facility. Its crew would need to manufacture replacement components from raw materials carried aboard, using fabrication equipment that itself degrades and must also be maintained and eventually replaced. This creates a recursive maintenance problem of disquieting depth. The machines that repair the ship also break down. The machines that repair those machines also break down. At some level in the chain, you reach tooling that cannot be replicated aboard because the ship does not carry the necessary raw materials, or because the fabrication equipment required to produce it has itself already failed. When that level collapses, the entire maintenance structure above it begins to deteriorate. Materials degrade, metals develop fatigue fractures, seals harden and crack, lubricants chemically decompose, electronics corrode, radiation damages circuitry at the atomic level. Micrometeorite impacts accumulate across the hull, each one negligible on its own, but collectively weakening structural integrity over the centuries. The ship does not face a single catastrophic failure. It faces the slow, patient erosion of every physical system simultaneously, spread across timescales so long that no individual generation can observe the full arc of decline. And yet, despite all of this, generation ships continue to appear in serious scientific literature as the most physically plausible path to interstellar settlement. The Initiative for Interstellar Studies, a UK-based non-profit, launched Project Hyperion in 2024 as a design competition, inviting multidisciplinary teams to envision generation ships for a 250-year crossing to a habitable exoplanet. The competition drew entries from researchers around the world. The winning design, named Chrysalis, proposed a cylindrical vessel approximately 36 miles long, carrying up to 2,400 people with rotating sections for artificial gravity and integrated agricultural systems for continuous food production. The competition had originally specified a population of 500 to 1,500, but the Chrysalis team argued that a larger population significantly improved long-term social and genetic stability. Entries were evaluated on engineering feasibility, social planning, cultural sustainability, and governance architecture. The very existence of this competition reveals something important about where the scientific community currently stands. The concept is taken seriously enough to draw institutional backing and rigorous interdisciplinary scrutiny. But the evaluation criteria also expose the depth of the problem. Entries were judged not only on propulsion and life support, but on how their civilizations would preserve knowledge, transmit culture, maintain governance, and manage psychological strain across centuries of confinement. The competition implicitly acknowledged what the elegant concept tries to conceal. A generation ship is not primarily an engineering problem, it is a civilization problem. And civilization problems do not yield to engineering solutions. You cannot weld social stability into a hull plate. You cannot install cultural continuity as a software update. You cannot bolt generational purpose onto a reactor casing. The hardware can be designed on paper. The human civilization that must operate it across centuries cannot be designed at all. And the silence surrounding that gap is where the real story of the generation ship begins. The generation ship is not a solution to the problem of interstellar distance. It is a transformation of that problem into something far more complex, far more fragile, and far more likely to fail in ways that no schematic can prevent. The distance between stars is immense, but the distance between launching a sealed civilization and successfully sustaining it across centuries may be immeasurably greater. What comes next examines exactly how severe that transformation becomes once you stop imagining the ship and start calculating the physics of what happens inside it. The ship has launched. Earth is gone, not obscured the way a coastline recedes from a departing vessel, fading gradually until distance swallows it. Gone in a way that has no equivalent in any human experience that has ever existed before. Within months of departure, the sun shrinks to a bright point, indistinguishable from thousands of other bright points. Within years, it becomes just another faint star in a field of faint stars. Within a decade, even that reference vanishes into the background noise of the galaxy. The ship is now the only world its passengers will ever inhabit. Everything they breathe, everything they drink, everything they eat must originate from systems that were sealed inside the hull at the moment of departure. Nothing enters from outside, nothing can be requested. The nearest possibility of rescue is receding behind them at whatever fraction of light speed the engines manage to achieve. And with every passing hour, the energy cost of reversing course and returning grows more prohibitive than pressing forward. There is no ambiguous return threshold. Within the first decade, turning back becomes practically impossible. The ship is committed, the people inside it are committed, and from this moment onward, every atom of oxygen, every molecule of water, every calorie of food aboard is the entirety of what will ever exist on this world. This is where the engineering reality of a generation ship diverges from every other machine humanity has ever assembled. A submarine can surface, a space station can receive resupply, an Antarctic research base can be evacuated. A generation ship operates under a constraint that has no precedent in the entire history of technology: total material closure sustained across centuries. The technical designation is a bioregenerative life support system, and the underlying concept is straightforward to describe while being nightmarish to execute in practice. Plants convert carbon dioxide into oxygen through photosynthesis, while simultaneously yielding food. Human and organic waste is broken down by microbial communities and cycled back into soil nutrients and purified water. Water itself is cleaned through filtration, condensation, and biological processing. The atmospheric mixture is continuously monitored and adjusted to hold the narrow range of gas concentrations that human physiology requires: approximately 21% oxygen, less than 1% carbon dioxide, a balance of nitrogen, and carefully regulated humidity. On paper, the cycle is elegant. Carbon, water, and nitrogen each trace closed loops. Atmosphere to plants, to humans, to waste, to microbes, and back again. Nothing is consumed in the chemical sense. Everything is transformed and returned. A well-engineered bioregenerative system could theoretically operate without limit, because it does not deplete its inputs. It merely reorganizes them. In practice, the word theoretically does catastrophic work in that sentence. Real bioregenerative systems do not close perfectly. They leak not through dramatic breaches, but through thousands of small inefficiencies that accumulate across time. Every airlock cycle releases a trace quantity of atmosphere. Every water purification pass leaves behind a fraction of contaminants that gradually concentrate in the reservoir. Every biological decomposition cycle produces trace compounds that are not completely broken down, slowly building up in the soil, the water table, or the breathable air. These losses are individually negligible. Over weeks or months they are unmeasurable. Over decades they become detectable. Over centuries they become existential. Consider oxygen alone. The human body consumes roughly 350 liters of oxygen daily at rest, and considerably more during physical exertion, with a working population averaging closer to 500 liters per person per day. A population of 1,000 people engaged in the continuous physical labor that ship maintenance demands consumes approximately 500,000 liters of oxygen every single day. This oxygen must be replaced entirely by photosynthesis, because there is no external atmosphere to draw from. The crops generating that oxygen require light, water, carbon dioxide, nutrients, and stable growing conditions. If yields drop by even a few percent through plant disease, soil nutrient imbalance, or a lighting system malfunction, the oxygen budget tightens immediately. The crew cannot simply breathe less. Their metabolic demand is set by biology, not by preference. The gap must be closed by the system, and if the system cannot close it, oxygen concentration begins to fall. We already know what happened when Biosphere 2 attempted exactly this kind of atmospheric equilibrium. Oxygen plummeted, carbon became locked into concrete, The most sophisticated sealed ecosystem humanity had ever constructed nearly killed its inhabitants within 2 years. But the specific lesson for a generation ship is considerably worse than the headline failure implies. Biosphere 2's atmospheric crisis was identified, diagnosed, and addressed because the team had direct communication with scientists on the outside. They could discuss the problem with atmospheric chemists and ecologists who were not trapped inside the enclosure. They could consult published research. They could request analytical instruments that had not been included in the original design, and ultimately, they could pump in outside air to prevent the oxygen deficit from crossing a lethal threshold. A generation ship crew facing an equivalent atmospheric anomaly would have none of these options. They would need to identify the problem using only the diagnostic instruments aboard. They would need to determine the cause using only the scientific expertise present in the current generation. They would need to devise and implement a solution using only the materials and equipment that have been aboard since departure. And they would need to accomplish all of this before the oxygen deficit reached lethal concentrations with no external consultation available and no emergency air supply waiting outside. The Biosphere 2 failure was recoverable because it occurred on Earth. The same failure aboard a generation ship 3 centuries into its voyage would be recoverable only if the crew happened to possess the specific knowledge, the appropriate equipment, and the correct materials to address it. If any link in that chain was broken through knowledge lost across generations, through equipment degradation, through material exhaustion, the failure would not be an experimental setback. It would be an extinction event confined to a metal container traveling through interstellar space with no one outside aware it was happening. A generation ship would encounter comparable surprises continuously across its entire operational lifetime. No matter how exhaustively pre-launch testing is conducted, complex ecosystems produce emergent behaviors that cannot be predicted from the properties of their individual components. The interaction between 10,000 species of microorganisms, dozens of food crops, recycling filtration systems, atmospheric chemistry, and the metabolic output of a human population creates a web of interdependencies so intricate that modeling it completely exceeds the capacity of any existing simulation. Each generation of crew will encounter failure modes the previous generation never witnessed because the system's slow chemical and biological drift creates new conditions on timescales longer than any individual human lifespan can observe. Water recycling presents its own cascade of compounding difficulties. A closed water system must purify every drop consumed by the crew and every volume used in agriculture, metabolic wastewater, agricultural runoff, atmospheric condensation, and industrial process water. NASA's water recovery systems aboard the International Space Station now reclaim approximately 98% of water from urine and cabin humidity, a milestone the agency announced in 2023. This is a remarkable achievement for a station that still receives regular resupply, but it means that 2% of processed water is still lost with every cycle. For a generation ship with no resupply capability, that 2% loss is a death sentence extended across a long enough timeline. Even at the current 98% recovery rate, cumulative losses would significantly deplete total water reserves within a few decades of continuous operation if no countermeasures existed. A generation ship would require water recovery rates approaching 99.9% or higher, sustained without interruption. The purification systems achieving that recovery rate would themselves demand maintenance, filter replacements, membrane cleaning, component repairs. The chemical or biological agents used in purification would need to be manufactured aboard from raw materials carried since launch. The energy required for continuous water processing would represent a substantial fraction of the ship's total power budget. And any disruption in the water recycling chain, whether from equipment failure, chemical contamination, or microbial interference, would begin depleting the single most critical resource aboard within days. Food production cannot rely on stored provisions. Even under ideal preservation conditions, no food storage technology can maintain nutritionally complete, edible supplies across centuries. Freeze-dried meals lose nutritional value over years. Canned goods degrade over decades. The ship must grow virtually everything its population eats from living agricultural systems operating without interruption for the entire voyage. These farms face constraints that no terrestrial agriculture has ever confronted. There is no weather, no seasons, no wild insect pollination, no natural soil replenishment from decomposing organic matter accumulated over millennia. Every parameter must be artificially controlled lighting, tuned to photosynthetically active wavelengths, temperature calibrated for each crop variety, nutrient solutions continuously adjusted, pollination performed mechanically or by managed insect colonies, pest control maintained without chemical pesticides that would contaminate the closed water and air systems. Crop diversity is not optional. Human nutrition requires a broad spectrum of vitamins, minerals, amino acids, and fatty acids that no single plant provides. A generation ship must cultivate grains, legumes, vegetables, fruits, and viable protein sources, fish perhaps, or insects, or cell-cultured tissue. Each of these agricultural systems carries different requirements for light intensity, water volume, temperature range, nutrient composition, and growing cycle duration. Managing this complexity in a sealed environment with zero tolerance for total crop failure represents an agricultural engineering challenge that surpasses anything attempted in controlled environment agriculture anywhere on Earth. And crops fail on Earth with regularity. Farmers respond by rotating to different varieties, importing replacement seeds, or allowing fields to rest and recover. A generation ship cannot import seeds. It cannot rest its agricultural area because the population requires food every day without exception. A pathogen that enters the wheat section will reach the rice section because the entire agricultural area exists within a single enclosed volume where air, water, and organisms circulate continuously. Geographic quarantine, the most reliable tool terrestrial agriculture possesses against disease spread, is a matter of degree aboard a sealed vessel, not a meaningful barrier. Now, add radiation. Beyond Earth's protective magnetosphere, space is saturated with ionizing radiation from two primary sources. Solar particle events produce intense bursts of protons and heavier atomic nuclei during solar flares and coronal mass ejections, periodic events that become more frequent during solar maximum cycles and are partially predictable, with sufficient warning systems. The second source is galactic cosmic radiation, a constant, omnidirectional background of extraordinarily energetic particles originating from supernovae and other violently energetic events distributed throughout the galaxy. Galactic cosmic rays consist predominantly of protons, but approximately 1% are heavy ions, ion nuclei, for instance traveling at relativistic velocities. These heavy ions carry kinetic energy on a scale that makes conventional shielding deeply problematic. Aluminum, the structural material of most spacecraft, actively worsens the problem for galactic cosmic radiation. When a high-energy heavy ion strikes an aluminum hull plate, it undergoes nuclear spallation, shattering into a cascade of secondary particles including neutrons, protons, lighter ions, and gamma rays. This secondary shower can be biologically more damaging than the original particle that produced it. The crew is exposed not merely to galactic cosmic rays, but to the secondary cascades those rays generate by interacting with the ship's own structure. Hydrogen-rich materials such as polyethylene or water provide meaningfully better shielding because hydrogen nuclei absorb incoming proton energy more efficiently without generating as many secondary particles. Several design proposals suggest surrounding habitat sections with water storage tanks that serve the dual purpose of shielding and water reservoir. This approach helps against solar particle events, but the highest energy galactic cosmic ray particles carry so much kinetic energy that no practical thickness of any passive shielding material stops them entirely. An ion nucleus traveling at 90% of light speed will penetrate meters of water or polyethylene, depositing a trail of ionization damage through whatever biological tissue lies in its path. NASA estimates that astronauts on a Mars mission lasting approximately 3 years would accumulate a total radiation dose of roughly 1 sievert, associated with a 5% increase in lifetime cancer risk. A generation ship traveling for centuries would expose its population to cumulative doses far exceeding this level, unless shielding effectiveness far surpasses anything currently achievable. Magnetic shielding using powerful superconducting magnets to deflect incoming charged particles has been proposed as an alternative to passive mass shielding. The concept has theoretical merit, but it confronts formidable practical obstacles. The enormous continuous power requirements for maintaining strong magnetic fields across the full surface area of a large vessel, the difficulty of intercepting electrically neutral secondary particles such as neutrons through magnetic deflection, and the engineering challenge of designing and maintaining superconducting magnet systems that must function reliably for centuries without servicing. The radiation problem extends beyond elevated cancer rates. Research conducted at NASA's Space Radiation Laboratory has demonstrated that exposure to heavy-ion galactic cosmic radiation produces persistent structural changes in brain tissue and measurable cognitive impairment in animal models. Mice exposed to simulated galactic cosmic ray environments showed reduced hippocampal neurogenesis, impaired synaptic plasticity, and deficits in learning and memory that persisted for months following exposure. These findings suggest that long-duration exposure to galactic cosmic radiation may progressively degrade cognitive function in human crew members, impairing the precise mental faculties needed to operate and maintain the systems keeping them alive. Across multiple generations, radiation introduces a genetic dimension. Ionizing radiation damages DNA. Cellular repair mechanisms correct most damage, but some mutations escape repair and can be transmitted to offspring if they occur in reproductive cells. Over centuries of continuous exposure above terrestrial background levels, the ship's population would accumulate genetic damage at a rate significantly higher than a population living beneath Earth's protective magnetosphere. This does not mean the crew would transform into something unrecognizable. It means that background rates of heritable genetic disease, developmental abnormalities, and cancer predisposition would rise incrementally, with each generation placing a steadily heavier burden on medical systems that are themselves degrading, operated by a medical workforce that is itself becoming smaller relative to the growing patient population. The medical challenge extends of radiation-induced illness. A generation ship must function as its own complete healthcare infrastructure for every medical condition capable of affecting a human population across centuries. Trauma surgery for industrial and agricultural accidents, obstetric care for every birth, pediatric medicine for every childhood illness, dental care, ophthalmology, psychiatric treatment, infectious disease management, chronic disease management, geriatric care, and end-of-life palliative support. Every clinical specialty, every diagnostic capability, every surgical procedure, every pharmaceutical compound must be available aboard, or the population goes without. Modern medicine depends on a global supply chain of extraordinary complexity. A single course of antibiotics requires pharmaceutical manufacturing facilities capable of synthesizing active compounds, quality control laboratories capable of verifying purity and dosage, distribution networks capable of delivering the medication, and regulatory frameworks ensuring safety and efficacy across millions of patients. A generation ship must replicate the essential functions of this entire chain using only the equipment and raw materials present at departure. Pharmaceutical manufacturing aboard would require chemical synthesis equipment capable of producing hundreds of distinct active compounds from base chemicals, analytical instruments to verify the identity, purity, and potency of each compound produced, sterile compounding facilities to formulate drugs into tablets, injectable solutions, topical preparations, and other delivery forms, and pharmacological expertise to prescribe, dose, and monitor medications for a population whose physiology may gradually diverge from terrestrial norms due to radiation exposure, altered gravity, and the unique pathological landscape of a sealed environment. Surgical equipment presents its own replacement problem. Scalpel blades dull, suture materials are consumed. Imaging equipment, whether X-ray, ultrasound, or magnetic resonance contains components that degrade and must eventually be serviced or replaced with parts manufactured aboard. Anesthesia requires specific chemical compounds that must be continuously synthesized. Sterilization systems consume energy and chemical inputs. Every surgical procedure depletes the ship's medical inventory by a finite amount, and that inventory can only be replenished through onboard manufacturing of steadily increasing complexity. The training pipeline for medical professionals must function without interruption across every generation. Physicians require years of formal education and supervised clinical experience before they can practice competently. Aboard a generation ship, medical education must be delivered by the ship's existing physicians who are simultaneously providing care to the entire population. There is no teaching hospital to rotate through, no visiting specialists to learn from, no medical journals arriving from a global research community to update clinical knowledge. The ship's medical practice would gradually diverge from terrestrial medicine, developing its own body of clinical experience based on the unique conditions aboard, while potentially losing contact with advances in medical science that occurred on Earth after departure. If a novel disease emerges aboard the ship, whether from mutation of an existing pathogen, from an unanticipated interaction between the ship's microbial environment and the human immune system, or from a chemical contaminant accumulating in the closed environment, the medical team must diagnose it, characterize it, and develop a treatment protocol using only the diagnostic and research tools present aboard. There is no Centers for Disease Control to consult, no World Health Organization to coordinate a response, no global pharmaceutical industry to develop a targeted treatment. The ship's medical team is the entire global health infrastructure for their world. And their world is a sealed container where an airborne pathogen can reach every inhabitant within hours of its first appearance. The engineering systems themselves suffer radiation damage on these timescales in ways that compound every other vulnerability. Ionizing radiation degrades electronic components by displacing atoms within semiconductor crystal structures, altering the electrical properties of transistors and memory cells in ways that accumulate invisibly until a threshold is crossed. Radiation-hardened electronics tolerate higher doses than commercial components, but no electronic system is immune to cumulative radiation damage across centuries of continuous exposure. The ship's computing systems, sensor arrays, navigation instruments, communications equipment, and automated control processes would all experience progressive functional degradation. Replacing damaged electronics requires manufacturing new components aboard, which requires functioning fabrication equipment, which is itself subject to identical radiation damage. This is the recursive maintenance problem in its starkest possible form. Every system on the ship degrades through radiation damage, mechanical wear, thermal cycling, chemical corrosion, and material fatigue. Maintaining these systems requires tools, spare components, raw materials, and the technical knowledge to use all three effectively. The tools degrade, the spare components are finite. The raw materials are limited to what was loaded at departure, supplemented only by whatever can be reclaimed from decommissioned equipment. The technical knowledge must be transmitted intact across generations without distortion or omission. Consider a specific example that illustrates how quickly the chain collapses. The atmospheric recycling system includes centrifugal fans that circulate air through carbon dioxide scrubbers and oxygen concentrators. These fans contain bearings that wear over time. Replacing the bearings requires machined components manufactured to precise dimensional tolerances. The machining equipment itself contains bearings, cutting tools, and electronic controllers, all of which also wear and require maintenance. The cutting tools are fabricated from specialized alloys that must be smelted and formed aboard. The smelting furnace requires refractory ceramic linings that degrade with each use. At some point, the maintenance chain reaches a component that cannot be reproduced aboard, either because the necessary raw materials have been exhausted or because the fabrication equipment required to produce it has failed beyond recoverable repair. This is not a theoretical concern, it is a mathematical certainty. Every manufactured object has a finite number of possible replacements, given a fixed inventory of raw materials and fabrication capability. Over centuries, the population of replaceable components decreases in one direction only. The ship's material wealth can only diminish. Every irreversible material transformation, every component worn beyond recyclability, every trace element chemically locked into an unusable compound represents a permanent subtraction from the ship's total resource base. Advanced fabrication technology could partially address this. Three-dimensional printing systems already capable of producing complex metal and polymer components from feedstock materials could theoretically allow a generation ship to manufacture most replacement parts on demand. But the printers themselves require feedstock materials, energy, and maintenance of their own precision components. They become part of the same maintenance recursion. And certain critical materials, rare earth elements used in electronics manufacturing, specific isotopes used in medical imaging, specialized catalysts used in chemical processing, may be impossible to recycle or chemically substitute once the original supply is exhausted. Structural integrity compounds these concerns across truly long durations. The ship's hull simultaneously functions as a pressure vessel, a radiation barrier, a thermal boundary, and a structural frame. It must withstand internal atmospheric pressure pushing outward, the mechanical stresses of any rotational gravity system, thermal gradients between sun-facing and shadow-facing surfaces, and the cumulative impact of micrometeorites. In interstellar space, micrometeorite density is lower than within the solar system, but it is not zero. Over centuries of transit, the hull accumulates thousands of microscopic impacts, each creating a tiny crater, a stress concentration point, or a microscopic crack in the structural material. Metal fatigue is an insidious failure mode because it offers no visible warning until the moment of catastrophic fracture. Microscopic cracks propagate incrementally with each stress cycle. The component appears completely functional, then it fails suddenly and completely. Aircraft manufacturers manage fatigue through rigorous inspection schedules and mandatory component replacement intervals. A generation ship would require equivalent protocols maintained across every structural element, every pressure seal, and every rotating assembly continuously, for centuries. The rotation problem deserves careful attention because it determines the physical scale of the entire vessel before any other design consideration is even addressed. Artificial gravity through rotation is not a design preference. It is a biological necessity. Decades of research aboard the International Space Station have confirmed, without ambiguity, that prolonged weightlessness produces severe physiological deterioration. Bone density decreases by approximately 1 to 2% per month. Muscle mass atrophies despite rigorous daily exercise regimens. Cardiovascular function deconditions as the heart no longer works against gravitational resistance. Intracranial pressure increases, causing vision impairment that has affected a substantial proportion of long-duration ISS crew members. Immune function weakens, wound healing slows. These effects are clinically manageable for missions lasting 6 months to a year, because the astronauts return to Earth and physically recover. A generation ship population lives permanently in whatever environment the ship provides. Their children are born into it. Their skeletal systems develop within it. Their cardiovascular architecture adapts to it. If the artificial gravity is insufficient, every generation grows up with bodies calibrated to conditions that will not match the planetary surface they are theoretically traveling toward. The physics of rotational gravity impose a severe constraint on minimum ship dimensions. The centripetal acceleration that simulates gravitational force depends on two variables, the rotation rate and the radius of rotation. Producing one full Earth gravity at a habitat radius of 100 meters requires rotation at approximately 3 revolutions per minute. This sounds manageable until the Coriolis effect enters the calculation. In a rotating reference frame, any object moving along the axis of rotation experiences a lateral deflection. For a person walking inside a rotating habitat, this manifests as a persistent sensation that the floor is tilting, that straight-line motion curves unexpectedly, and that the inner ear's balance signals conflict with what the eyes are reporting. The result is motion sickness, spatial disorientation, and impaired coordination. Research into human tolerance of Coriolis effects indicates that most people experience significant discomfort at rotation rates above approximately 2 revolutions per minute, and that sustained habitation becomes genuinely problematic above roughly 1.5 revolutions per minute for the general population, including children and elderly residents who are consistently more vulnerable than healthy young adults. Reducing the rotation rate to tolerable levels requires increasing the radius proportionally. To generate 1 Earth gravity at 1 revolution per minute, the habitat radius must reach approximately 900 meters. At half a revolution per minute, the threshold that most studies suggest would be comfortable for long-term habitation across all age groups, the required radius exceeds 3,500 meters, 3.5 kilometers. The rotating section of the ship must be at least 7 kilometers in diameter, simply to provide gravitational conditions that do not make its inhabitants chronically nauseated. This is not a spacecraft dimension. This is the scale of a city. A rotating habitat 7 kilometers across, structurally robust enough to maintain spin for centuries, pressurized against vacuum, shielded against radiation, and mechanically coupled to the non-rotating sections of the vessel through bearing assemblies that must bear the full rotational load indefinitely, with dimensional tolerances measured in fractions of a millimeter across structures spanning kilometers. The structural mass required for such a habitat is staggering, and every kilogram of that mass must be accelerated to interstellar velocity, which means every kilogram demands additional propulsion energy. The generation ship grows larger, not because its designers want luxury, but because human biology sets a minimum habitat radius below which long-duration habitation produces irreversible medical deterioration. The ship is enormous because it must be, and its enormity multiplies every challenge it already faces. More structure means more material susceptible to fatigue. More pressurized volume means more atmosphere requiring continuous maintenance. More surface area means more hull exposed to micrometeorite impact and radiation. More rotating mass means more energy consumed sustaining spin. The ship grows larger, the margin for failure does not grow at all. And there is the question of what happens if the rotation stops entirely. A bearing seizure, a structural fracture at the rotational joint, a power failure in the spin maintenance systems. Any of these events would begin decelerating the habitat section, reducing artificial gravity over hours or days. The population would experience a gradual transition toward weightlessness, accompanied by the immediate failure of every system designed to function in a gravitational environment. Water no longer flows through agricultural irrigation channels by gravity. Soil no longer remains in planting beds. The atmospheric convection patterns that distribute heat and humidity throughout the habitat cease functioning. Fires, if they occur, behave unpredictably in reduced gravity, forming spherical flame fronts that are harder to detect by conventional sensors and significantly more difficult to suppress. A loss of rotation is not merely an inconvenience. It is a simultaneous systemic crisis affecting agriculture, water management, atmospheric circulation, fire suppression, and human health at once. Restarting rotation after a complete stoppage requires enormous energy input and must be executed gradually to avoid imposing torque loads on structural connections that were not designed to withstand sudden angular acceleration. The process could require weeks or months, during which the entire population lives in degraded gravitational conditions that accelerate bone loss, muscle atrophy, and cardiovascular deconditioning. If rotation cannot be restored at all, the mission has effectively ended, not because the ship has been destroyed, but because the population's long-term physiology has become incompatible with the physical demands of arrival and planetary colonization. The energy budget of a generation ship makes the operational margins unmistakably clear once every major continuous power demand is placed alongside the others. Agricultural lighting alone represents an enormous and unavoidable expenditure. Plants require light intensities comparable to full sunlight for productive photosynthesis, approximately 1,000 watts per square meter of growing area for the most calorie-dense crops. If the ship must feed a population of 20,000 people from intensive indoor agriculture, the required growing area could span hundreds of thousands of square meters, each demanding high-intensity lighting for 12 to 16 hours per day. Agricultural lighting alone could consume hundreds of megawatts on a continuous basis. Atmospheric processing adds another major load. Carbon dioxide scrubbers, oxygen concentrators, humidity controllers, temperature regulation systems, and air circulation fans operate continuously across the entire pressurized volume. Water purification systems pump, filter, distill, and chemically treat every liter consumed and every drop of agricultural and industrial runoff without pause. Waste processing systems decompose biological and industrial waste through microbial digestion, thermal treatment, and chemical conversion, each stage consuming energy. Maintaining rotation requires continuous input to overcome friction in bearing assemblies. Fabrication equipment draws power at high peak loads. Medical systems, communications infrastructure, computing networks, residential and workspace lighting, and the thermal management systems that prevent the ship from freezing in the interstellar void all add to the baseline continuous demand. A conservative estimate for the total continuous power requirement of a generation ship supporting 20,000 people falls in the range of 1 to several gigawatts, comparable to the output of a large terrestrial nuclear power plant. But a terrestrial nuclear power plant operates within a national grid that includes backup generation, fuel supply from external mining and enrichment facilities, and a maintenance workforce drawn from a national population of millions. A generation ship must produce this power from reactors that carry no external fuel supply, connect to no backup grid, and depend on a maintenance workforce drawn entirely from a population whose total size may be 10,000 people, of whom only a fraction in any given generation will possess relevant nuclear engineering expertise. Modern nuclear power plants have operational lifespans of 40 to 60 years, with extensive maintenance and periodic refueling from external fuel fabrication facilities. A generation ship reactor would need to sustain output for 5 to 10 times that duration without any external fuel supply. Breeder reactor designs that produce new fissile material from fertile isotopes could theoretically extend the fuel cycle, but breeder technology introduces additional engineering complexity, additional failure modes, and additional radiological hazards that themselves require specialized maintenance expertise to manage safely. If reactor output declines by even a modest percentage through fuel depletion, component degradation, or a maintenance shortfall, in any given generation, the power deficit must be rationed across all competing demands. Which system receives less? The agricultural lighting, the water purifiers, the atmospheric processors, the medical equipment. Every reduction in power to any one system produces downstream consequences that propagate through the ship's interconnected infrastructure. A 5% reduction in agricultural lighting reduces crop yields. Reduced crop yields mean less food and diminished oxygen production. Reduced oxygen production increases the load on atmospheric processing systems. Increased atmospheric processing load demands more power from reactors already running at reduced output. The deficit deepens, the spiral tightens. And every one of these challenges atmospheric chemistry, water cycling, food production, radiation shielding, structural maintenance, power generation operates simultaneously, interacts with every other challenge, and does so continuously, without pause, for the full duration of the voyage. A failure in the power system reduces energy available for water purification and atmospheric processing. A failure in atmospheric processing degrades crop yields. Reduced crop yields affect crew nutrition, which affects crew health, which reduces the workforce available for maintenance. Reduced maintenance capacity accelerates the degradation of all other systems. The failure modes are not independent, they are coupled. And in closed systems, coupled failure modes do not produce linear decline. They produce cascades. A cascade begins when one system's partial failure increases the stress on adjacent systems, pushing them toward their own failure thresholds. If a second system fails under that elevated load, the remaining systems absorb greater stress still. Each successive failure accelerates the next. The cascade advances not at the pace of the original failure, but at an accelerating rate that can overwhelm the crew's capacity to respond before they have fully understood what they are responding to. On Earth, cascading failures in complex systems produce power blackouts, industrial accidents, and infrastructure collapses. In every such case, the cascade is eventually arrested by external intervention replacement equipment delivered from outside the affected system, emergency personnel arriving from neighboring jurisdictions, resources imported from unaffected areas. Aboard a generation ship, external intervention does not exist. There are no neighboring jurisdictions. There are no unaffected areas. The cascade either stops because the crew manages to arrest it, using only the knowledge and resources already aboard, or it continues until it reaches a system whose failure is incompatible with crew survival. The oxygen stops flowing, the water stops being purified, the food stops growing, the hull fails. Any one of these endpoints is fatal, and the margin separating a manageable partial failure from a fatal cascade may be considerably narrower than any design team can predict before departure. The engineering reality of a generation ship is not one dramatic challenge that determined people can heroically overcome. It is an accumulation of slow erosions, each individually survivable in the short term, collectively lethal across the timescales involved. The ship does not explode. It does not collide with anything in a cinematic fireball. It slowly, incrementally, inevitably runs down like a clock with no one to wind it, sealed in a room with no door to the outside. And everything described so far assumes something that has not yet been questioned. It assumes a crew that is competent, motivated, socially unified, and unwavering in its commitment to maintaining the systems. It assumes that the people aboard possess the technical knowledge to identify failures, the manufacturing capacity to fabricate replacements, and the social cohesion to allocate resources and labor effectively across the entire population, across all the generations that follow. It assumes, in other words, a functioning civilization. What happens when that assumption fails is where the generation ship concept encounters its deepest and most terrifying challenge. Because the machine can be drawn on paper, the people who must operate it across centuries cannot be drawn at all. Every challenge examined so far assumes something that has never existed. A human population that remains perfectly cooperative, technically capable, socially coherent, and psychologically intact across centuries of sealed confinement with no external contact, no possibility of escape, and no freedom of choice regarding any of it. The engineering problems are severe. The ecological problems are potentially fatal. But both categories share a common property. They can, at least in principle, be modeled, tested, and designed against using the established languages of physics, chemistry, and biology. The human problems that a generation ship must solve cannot be modeled with equivalent precision because they involve the one variable that no equation has ever reliably predicted: how people behave when they are trapped. The population question arrives first, because it constrains every other decision before the first hull plate is welded into position. A generation ship cannot carry an arbitrary number of people. Every additional person demands more oxygen, more water, more food, more living space, more waste processing capacity, and more mass that must be accelerated to interstellar velocity. The energy cost of the entire mission scales with the total mass of the vessel, and the life support infrastructure that each person requires constitutes a significant fraction of that mass. Every design incentive pushes toward minimizing the population, but genetics imposes a hard floor on how small that population can responsibly be. When a group of people reproduces in isolation across many generations, two related biological processes erode genetic health in parallel. The first is genetic drift. In any population, gene variants are maintained across generations only if enough carriers exist to reliably pass them forward. In a small population, variants can simply vanish by chance, not because they are harmful, but because the individuals carrying them happened not to reproduce in a particular generation, or reproduced fewer times than chance might otherwise have allowed. Over successive generations, Drift strips away genetic diversity the way wind strips loose soil from an exposed hillside, slowly, invisibly, and then suddenly, catastrophically. The second process is inbreeding. In a small closed population, all individuals become biologically related within a handful of generations. Mating between relatives increases the probability that any given offspring inherits two identical copies of the same recessive gene variant, including harmful ones that cause no problems when paired with a functional copy, but produce severe developmental consequences when both copies are defective. The accumulated effects compound with each generation. Reduced fertility, elevated infant mortality, higher rates of congenital disease, weakened immune response. These outcomes have been documented thoroughly in isolated human communities that have persisted on Earth. The Pitcairn Islanders, descended from 9 bounty mutineers and 18 Polynesian companions who settled the island in 1790, maintained a population of roughly 50 to 200 people for more than 2 centuries. They survived, but medical surveys of the community revealed elevated rates of specific genetic conditions consistent with founder effect and inbreeding in a small, closed population. The inhabitants of Tristan da Cunha, the most geographically remote, permanently inhabited island on Earth, descended from 15 original settlers and after 2 centuries showed markedly elevated rates of asthma traceable to 3 founding individuals who carried the genetic predisposition. Both of these communities survived in part because they were not entirely sealed. Occasional arrivals of new settlers introduced fresh genetic material that partially counteracted the inbreeding effects accumulating in each successive generation. A generation ship has no equivalent mechanism, zero. The founding population is the entire gene pool for the full duration of the voyage. No new genetic material enters the system until arrival at the destination, which may be centuries away. This makes the genetic constraints far more severe than any terrestrial island analogy suggests, because every terrestrial island analogy involves at least occasional contact with the outside world. Anthropologist John Moore estimated that a minimum founding population of approximately 160 people carefully selected, age-balanced across reproductive cohorts, and organized according to enforced mating protocols, specifically designed to minimize inbreeding, could sustain adequate genetic diversity across a 200-year voyage. But Moore's figure rested on assumptions of optimal social compliance across every generation. Every individual follows the prescribed reproductive pairing guidelines without deviation. No catastrophic population losses occur through disease, accident, or conflict. The social engineering required to enforce reproductive behavior across centuries actually functions as designed. Each of these assumptions is, individually, historically implausible. Anthropologist Cameron Smith challenged Moore's optimistic projection in research conducted for Project Hyperion. Smith's analysis incorporated realistic assumptions about demographic variability, the statistical likelihood that some individuals in every generation would not reproduce due to infertility, personal choice, or premature death, and the mathematical probability that the population would experience at least one significant mortality shock across a multi-century voyage. His models suggested that a genetically viable founding population for a multi-generational interstellar voyage would need to fall somewhere between 14,000 and 44,000 people, with a recommended working figure of approximately 20,000 to 40,000, not because the theoretical minimum is that large, but because real populations experience shocks, epidemics, accidents, localized disasters within the ship, and a population must be large enough to absorb those shocks without falling below the threshold of long-term genetic viability. Consider what a population of even 20,000 people, the lower boundary of Smith's recommended range, actually requires of the vessel carrying them. 20,000 people need living space, working space, recreational space, agricultural space, industrial space, medical facilities, educational institutions, and governance infrastructure of sufficient complexity to manage a small city. They generate waste at city scale, they consume resources at city scale, they produce social conflicts, political disagreements, criminal behavior, mental illness, and interpersonal violence at rates consistent with any human community of equivalent size. 20,000 people are not a crew, they are a city. And cities on Earth, with all the advantages of open air, natural ecosystems, external trade networks, and the fundamental psychological reassurance that the world extends indefinitely beyond the city's borders, still experience crime, political instability, resource disputes, factionalism, and periodic social collapse. The history of human urban settlements is not a story of stable, cooperative communities functioning harmoniously across centuries. It is a story of continuous tension, negotiation, eruption, and reconstruction. A generation ship carrying 20,000 people must govern that population under conditions of absolute material constraint and permanent confinement. And the governance structure required must persist across centuries, with no external source of legitimacy, no comparative electoral framework, no release valve of emigration for dissatisfied groups, and no possibility of territorial secession by factions unwilling to submit to the prevailing authority. Every political system humanity has ever devised relies on at least one of these pressure valves to survive. Democracies function partly because dissatisfied citizens retain meaningful options. They can vote, organize opposition, protest publicly, seek asylum elsewhere, or simply leave. The knowledge that alternatives exist moderates the intensity of political conflict, because losing an election does not mean permanent subjugation. Aboard a generation ship, losing a political contest means permanent subjugation because there is nowhere to go and no outside power capable of intervening. If the governance system is democratic, an additional problem emerges that no political theorist has yet resolved satisfactorily. What happens when a majority of the population, perhaps in generations 7 or 8, people who were born aboard and have no personal connection to Earth or to the destination, votes to abandon the mission entirely, to stop accelerating toward the target star and simply continue living aboard the vessel indefinitely? The founding generation designed the mission. The 7th generation inherited it. What moral authority does the founding generation hold over the political decisions of their distant descendants? Across centuries on Earth, constitutions are amended, governing philosophies are overturned, revolutions occur. The political commitments of one generation do not permanently bind the next, because future generations retain the physical capacity to choose differently. A generation ship, whose mission cannot be altered by its inhabitants, is a dictatorship of the dead imposed upon the living. A generation ship whose mission can be altered by its inhabitants may find that mission abandoned by people who feel no authentic connection to a destination chosen by ancestors whose names they may not even remember. If the governance system is authoritarian, the standard pathologies of concentrated power are amplified dramatically by the conditions of confinement. Power corrupts in environments where it cannot be effectively challenged. Aboard a generation ship, concentrated authority cannot be challenged through any external mechanism because there is no external mechanism of any kind. Oppressed populations on Earth can seek refuge across national borders, appeal to international institutions, or receive material support from foreign allies sympathetic to their situation. Oppressed populations aboard a generation ship have no borders to cross, no international institutions to petition, and no outside allies who are even aware of their existence. A tyrannical governing council aboard an interstellar vessel cannot be removed by external pressure. It can only be removed from within, which means through internal conflict, with consequences that unfold inside a sealed container where violence threatens the infrastructure keeping everyone alive. Religious or ideological governance has been proposed as a more durable foundation for multi-century institutional persistence. Several generation ship design studies have suggested organizing the mission around a shared philosophical or spiritual framework robust enough to provide social cohesion across generations, grounding authority in transcendent principles rather than in the personalities or competence of individual leaders. History offers partial encouragement for this idea. The Benedictine monastic tradition, founded in the 6th century, persists today. Certain Jewish communities maintained cultural and religious identity across millennia of geographic dispersal. Some religious orders have sustained recognizable institutional identity for longer than most nations have existed. But every one of these examples survived within a larger civilization that provided economic support, cultural context, and a continuous flow of new members who chose to join voluntarily. A shipboard religious community would exist in conditions of total isolation, with no broader civilization to provide context or renewal, no influx of converts to refresh institutional vitality, and no competing traditions to sharpen doctrinal clarity through contrast. The same three fates that have eventually overtaken every truly isolated religious community in recorded history would await it: intellectual stagnation. As the community loses contact with the broader development of human thought and doctrine, calcifies into unrevisable dogma. Doctrinal schism, as internal disagreements about interpretation escalate into irresolvable conflict in the absence of any external authority capable of adjudication, or simply gradual dissolution, as the framework loses its capacity to generate felt meaning for people whose lived experience has drifted so far from the framework's founding assumptions that the original narrative no longer resonates. Cultural transmission compounds every governance challenge by introducing a vulnerability that operates invisibly across generational time. The skills, knowledge, and institutional memory required to maintain the ship must pass from each generation to the next without meaningful degradation. This is not limited to technical knowledge about reactor maintenance procedures or atmospheric chemistry calibration. It encompasses the entire framework of social norms, historical understanding, and mission context that gives the voyage coherent structure and purpose. On Earth, cultural transmission occurs through a vast, redundant ecosystem of institutions: schools, universities, libraries, museums, professional associations, apprenticeship networks, media organizations, religious traditions, and informal community bonds all contribute to preserving and transmitting knowledge across generations. These institutions are redundant in the engineering sense. If one fails, others compensate. If a university closes, its accumulated knowledge persists in the memories of its graduates, in the books its faculty produced, in the competing institutions that absorbed its researchers, and in the broader intellectual culture that those researchers helped to shape. A generation ship must replicate these functions with a fraction of the institutional infrastructure, with zero redundancy available from external sources, and with a population too small to sustain the specialization that redundant knowledge transmission requires. The fragility of knowledge transmission in truly isolated communities has been documented in circumstances that offer uncomfortable precedents. The Aboriginal peoples of Tasmania, separated from the Australian mainland for approximately 10,000 years after rising sea levels severed the land connection, gradually lost several technologies their ancestors had possessed. Bone tool manufacturing disappeared. Cold weather clothing construction was apparently abandoned. Some researchers have argued, though the point remains debated among anthropologists, that the ability to independently initiate fire was also lost. This technological regression did not occur because the Tasmanians were less capable than their mainland counterparts. It occurred because their small, isolated population could not maintain the full breadth of specialized knowledge that a larger, interconnected population preserves through distributed expertise and overlapping transmission pathways. When specialists died without fully trained replacements, specific knowledge narrowed and eventually vanished. A generation ship faces structurally identical risks across every domain of critical technical knowledge. Specialized expertise is maintained by specialists. If the ship's nuclear engineering team consists of 5 or 10 people in a given generation, and a disease outbreak or a structural accident kills several of them before they have completed training their successors, that expertise is diminished or lost. The loss may not manifest immediately. The reactor continues operating on its existing maintenance schedule, but when a novel failure mode appears 2 generations later, the crew may lack the deep institutional knowledge required to diagnose and address it, because the chain of expert transmission was broken decades earlier by events that seemed at the time, to be survivable local tragedies rather than civilization-level catastrophes. Language itself will drift in ways that carry direct operational consequences. Linguists have established that all living languages change continuously through phonological shifts, grammatical evolution, vocabulary development, and semantic transformation. The rate of change accelerates in isolated populations because smaller communities have fewer speakers to enforce conservative linguistic norms and no contact with external language communities to provide stabilizing pressure. Research conducted in the context of generation ship design studies has estimated that a sealed shipboard population would develop a recognizably distinct dialect within a few generations, and a potentially mutually unintelligible language variant within 10 to 20 generations. This linguistic drift is not merely a cultural curiosity. It carries direct consequences for operational continuity. Technical documentation written by the founding generation operating manuals, engineering specifications, safety procedures, maintenance protocols, medical reference materials would become progressively more difficult for later generations to read fluently. The documents that encode the most critical knowledge for maintaining the ship would gradually transform into archaic texts, requiring active translation rather than direct comprehension. Unless the ship maintains a rigorous and continuously enforced program of language standardization across centuries, the technical literature, preserving the knowledge most essential to survival, would slowly become inaccessible to the very people whose lives depend on understanding it. Children complicate the generation ship in ways that no other category of inhabitant does, because children must be formed entirely by the environment the ship provides. An adult who boarded at launch carries memories of Earth, of open landscapes, of weather that was not engineered, of cultural variety extending beyond any single community, of a world with horizons that recede rather than terminate at a wall. A child born in the fourth generation carries none of this. Their entire cognitive and emotional development occurs within the ship's interior. Their concept of normal is the ship. Their understanding of physical reality is shaped by artificial environments, recycled atmosphere, engineered lighting cycles, and a social universe bounded by the same several thousand faces they have known since infancy. Developmental psychology has established through extensive research that children's cognitive and emotional growth is profoundly shaped by environmental richness. Exposure to natural environments improves attentional regulation and supports the development of spatial reasoning and creative thinking. Variety in social interactions builds theory of mind, the capacity to understand that other people hold perspectives and beliefs genuinely different from one's own. Exposure to diverse cultural practices fosters the cognitive flexibility that enables adaptive problem-solving in novel situations. A generation ship can attempt to simulate some of these inputs through carefully designed green spaces, varied architectural environments, and structured social programs. But the simulation is bounded by the ship's finite physical volume and its fixed population. A child growing up aboard will never see a horizon. The longest unobstructed sightline within even a very large rotating habitat might extend a few hundred meters. They will never experience weather that was not deliberately programmed into the environmental control systems. They will never encounter an animal that was not intentionally included in the ship's managed ecosystem. They will never meet a stranger in any meaningful sense of that word, because every person aboard is part of the same small community and has been known at least by reputation since before the child's birth. The educational challenge is more acute still. The ship requires every generation to produce a specific distribution of skilled professionals in approximately the right proportions: life support engineers, agricultural specialists, nuclear technicians, physicians, fabrication machinists, computer systems administrators, teachers, governance personnel. The population is far too small to sustain a free labor market where individuals select careers based primarily on personal interest and aptitude. The ship needs specific roles filled in specific numbers, and educational systems must be designed to channel children toward those roles, whether or not the children find them compelling. On Earth, educational systems can absorb significant inefficiency because the economy is large and diverse enough to accommodate people who change directions, pursue impractical interests, or take years to find their professional footing. A generation ship cannot afford this flexibility. If too few children in a given generation develop expertise in nuclear engineering, the reactor maintenance team is understaffed in the generation that follows. If too many children pursue interests in art, philosophy, or humanistic inquiry at the expense of technical training, the ship's operational capacity begins to degrade in the generation after that. Education aboard a generation ship is not a pathway to personal development. It is a resource allocation mechanism, and children are the resource being allocated. This creates a tension between individual freedom and collective survival that no educational philosophy has ever resolved cleanly. Allow children to follow their genuine interests and risk critical skill shortages that emerge a generation later, when the consequences of the shortage are no longer correctable, or assign educational tracks based on aptitude testing and current operational needs, producing a technically capable workforce at the direct cost of personal autonomy and the intrinsic motivation that makes competence sustainable across a lifetime. The first approach risks the ship's physical survival. The second risks producing a population of resentful workers performing duties they did not choose, and resentment, in a closed system with no exit, does not dissipate, it accumulates. Teaching children about the destination presents its own insoluble pedagogical problem. How do you convey the significance of a planet that no living person has visited, a world that exists only as data in astronomical records compiled by people who died before any child aboard was conceived? How do you motivate a 12-year-old to care about a star system they will never personally reach when the world they actually inhabit, the ship, with its familiar corridors and recycled air and artificial sunlight, is the only reality they have ever touched? How do you prevent the destination from becoming an abstraction so thoroughly removed from daily felt experience that it loses all motivational force entirely? Terrestrial education draws constantly on experiential reference points. A geography lesson invokes landscapes the student might someday walk through. A biology lesson can be supplemented by time spent in a forest or by the side of a river. A history lesson describes events that occurred in places that still exist and can be traveled to. Aboard a generation ship, every reference to the world outside the hull is second-hand at best. Every description of an ocean, a mountain range, a thunderstorm, or the sensation of standing under an open sky is mediated through recordings, simulations, and inherited narratives passed down through people who have themselves never experienced the things they are describing. The educational system must somehow transmit not merely information, but felt significance about realities that no living person aboard has directly experienced. If that transmission fails, if the destination becomes just a word in a curriculum rather than a genuine aspiration that shapes behavior and motivates sacrifice, then the motivational foundation of the entire mission begins to erode at its deepest level. The adults who eventually abandon the mission were once children who were never given a reason to believe in it that felt real enough to hold. The mission does not die in a single dramatic moment of collective repudiation. It dies quietly, in a classroom, when a child asks why they should care about a star they will never see, and the teacher does not have an answer that resonates beyond the repetition of inherited doctrine. Mission drift is the overarching term for all of these converging processes, and it may be the single most statistically probable mode of failure for any generation ship that successfully navigates its engineering challenges. Mission drift occurs when the original purpose of an institution gradually shifts, dilutes, or disappears, as the people responsible for carrying it forward are replaced by successors with different experiences, different priorities, and different relationships to the founding narrative. Every long-lived institution on Earth has experienced mission drift of some kind. Universities established to train clergy now produce engineers and economists. Military orders founded to pursue religious warfare now operate hospitals and schools. Colonial outposts established for resource extraction eventually became independent nations with no meaningful allegiance to the founding power that sent them. On Earth, these transformations are not failures. They represent healthy institutional adaptation to changing circumstances and evolving human needs. Aboard a generation ship, mission drift is catastrophic, because the mission is the reason the ship exists at all. If the 8th generation no longer understands, internalizes, or assigns priority to reaching the target star, the entire justification for the voyage dissolves. The ship ceases to be an ark carrying humanity toward a new world and becomes instead a sealed habitat, drifting through interstellar space with no purpose beyond its own continuation. And continuation without purpose generates its own form of civilizational crisis. Human beings derive meaning from goals, from narratives that explain suffering and justify sacrifice. The founding generation possesses such a narrative in full force. They are pioneers. Perhaps, if the mission was framed as a survival necessity, they believe the future of the species depends on what they are doing. They chose this. They feel it. They can endure hardship because they understand with felt conviction why it is necessary. Their children inherit a diminished version of this narrative. They were raised on the mythology of the mission. They heard the stories, but they never stood on Earth. They never experienced sunlight that was not produced by an electrical system. They never breathed air that was not filtered and recirculated. The destination is an abstraction taught in classrooms, not a reality felt in the body. Their commitment to the mission is inherited, doctrinal secondhand in the precise sense that it was transmitted rather than discovered. By the 5th or 6th generation, the narrative has become mythology in the anthropological sense of that word, a foundational story that explains the community's origins and purpose, but which may or may not be taken literally, and which different members of the community will interpret with widely varying degrees of personal investment. Some inhabitants will hold the mission as a genuine, motivating commitment. Others will regard it as a tradition to be respected without being lived. Still, others may actively reject it, arguing that the ship is their home, the only home any of them have ever known, and that the destination is irrelevant or unnecessarily dangerous, or simply less meaningful than the life they have already built. Why risk everything on an alien world when the ship has sustained human life for generations? Why change what demonstrably works? This is not speculative psychology. It is the documented behavior of every long-duration isolated community in recorded human history. The Polynesian voyaging cultures that settled the Pacific Islands maintained their extraordinary navigation knowledge only as long as active, intentional voyaging continued. When island populations became self-sustaining and the compelling imperative to explore diminished, navigation knowledge was lost within a few generations, surviving in oral tradition as ceremony and myth rather than as living practice. European explorers eventually encountered communities that preserved ancient double-hulled canoe designs in their cultural memory, but had no living practitioners capable of building or navigating them. The knowledge had become story. The story was no longer skill. A generation ship faces the same trajectory, unfolding across a far more consequential domain. The skills required for a rival planetary atmospheric survey, orbital insertion, surface entry, initial colony construction are not the skills required for the voyage itself. If the crossing lasts 10 or 15 generations, arrival capabilities have no practical application for centuries. They exist only in training programs, in documentation, and in the accumulated institutional memory of people who are teaching skills they themselves have never been required to exercise in any operational context. Maintaining genuine proficiency in capabilities that will not be used for longer than most human civilizations have ever lasted requires a degree of sustained institutional discipline that has no precedent in the historical record. And the psychological burden of inherited exile deserves its own careful attention, because it operates at the level of the individual beneath all the institutional and cultural dynamics described above. Consider the inner life of a person born on a generation ship in, say, Generation 7. This person has never seen a planet, has never experienced weather, has never stood beneath an open sky, or felt the particular quality of silence that exists in a truly open landscape. Their entire existence has occurred inside a structure, approximately the volume of a small town, surrounded by walls beyond which lies instant death. Every person they will ever know already lives inside this same structure. Every experience they will ever have will occur within it. They will die within it. They did not choose this. They were born into it, the product of a reproductive decision made by parents living under constraints imposed by a mission designed by people who died before their parents were conceived. Their autonomy is bounded by the ship's resource limitations, by its governance structure, by the social expectations of a community from which no exit exists. They cannot freely change professions because the ship has specific needs that override individual preference. They cannot choose to have more or fewer children than the population management framework permits. They cannot leave the community and pursue a different life elsewhere. There is no elsewhere. On Earth, even prisoners know that the world continues beyond their cell walls. The psychological architecture of incarceration depends on the existence of an outside, a world that continues in the prisoner's absence, to which they might conceivably return. Generation ship inhabitants have no such outside to hold in mind. The ship is not a temporary confinement with a release date visible somewhere in the future. It is a permanent reality for them, as it was for their parents, and as it will be for their children. There is no parole. There is no world beyond the hull that exists within the reach of anyone alive. The psychological literature on extended confinement in isolated environments drawn from submarine deployments, Antarctic winter-over programs, and simulated long-duration space missions such as the Mars 500 experiment, in which 6 crew members spent 520 days in a sealed facility in Moscow, consistently identifies the same cluster of responses across studies: depression, interpersonal conflict escalating beyond what would be considered normal in open environments, social withdrawal, sleep disruption, cognitive impairment, and what researchers have termed third quarter syndrome, a characteristic motivational collapse that occurs approximately 3/4 of the way through a defined confinement period, when the endpoint is theoretically visible but still psychologically distant enough to produce a particular form of despair. These studies involve confinement periods ranging from roughly 6 months to a year and a half. The Generation ship demands confinement across an entire human lifetime, repeated without interruption across multiple successive lifetimes, with no endpoint visible to the vast majority of people who will ever live aboard. Extrapolating from studies of 6-month confinement to the psychological dynamics of permanent, multi-generational confinement is methodologically uncertain in its specifics. The qualitative nature of permanent confinement may differ fundamentally from the qualitative experience of temporary confinement in ways that existing research frameworks are not designed to capture. But the direction of every available piece of evidence points unambiguously in a single direction. Confinement degrades psychological function. Isolation amplifies interpersonal conflict. Scarcity intensifies competition for resources and social status. And the complete absence of external novelty, new places, new people, genuinely new experiences originating from outside the community, produces a flattening of affect and motivation that accumulates steadily across time without any natural mechanism of relief. Multiply these individual psychological burdens across a population of 10,000 people, project them across centuries, and what you have is not a crew operating a spacecraft under difficult conditions. What you have is a captive civilization under permanent and unrelenting strain, asked to maintain perfect technical discipline and social coherence for longer than most civilizations in human history have endured under vastly more favorable conditions. The historical record is unambiguous on this point. No human civilization has ever maintained stable governance, continuous cultural transmission, and unbroken institutional purpose for the duration required by even the shortest plausible generation ship voyage without undergoing transformation, disruption, or partial collapse. At least once along the way. The Ottoman Empire lasted more than 6 centuries, but survived through continuous territorial expansion, absorption of conquered populations, and periodic internal reform driven by contact with rival powers. The Catholic Church has persisted for roughly 2,000 years, but has experienced schisms, reformations, corruption scandals, and doctrinal revolutions that would have proven fatal in a sealed environment with no room for the kind of institutional competition that ultimately drives renewal. Chinese dynastic civilization maintained cultural continuity across millennia, but did so through a recurring cycle of collapse and reconstruction, each dynasty eventually replacing the last through war, internal dissolution, or revolution, with each reconstruction enabled by contact with a broader world that preserved knowledge and provided resources during periods of internal failure. Every long-lived civilization on Earth survived by remaining open, by absorbing external influences, by recovering from catastrophic internal disruptions through contact with neighboring cultures that had not experienced the same disruptions simultaneously, and by allowing its population the fundamental freedom to leave, freedom that both releases social pressure and continuously reminds the remaining population that their continued presence is a choice rather than a sentence. A generation ship permits none of these survival mechanisms. It is a closed system in every dimension simultaneously, materially, socially, culturally, and psychologically. The very qualities that have made civilizations resilient across centuries of terrestrial history are precisely the qualities that a sealed interstellar vessel cannot by definition possess. The ship's engineering may function perfectly, the reactors may sustain their output, the atmosphere may remain breathable, the crops may grow, the water may flow clean, and inside this functioning machine, the civilization it was built to carry may slowly, quietly, and without any single dramatic crisis, come entirely apart. Not through catastrophe, through the accumulated weight of isolation, confinement, drift, and the unbearable inheritance of a mission that belongs to the dead imposed without consent upon the living. Everything we have examined so far has followed a single trajectory, a narrowing. The ecological margins tighten, the engineering tolerances shrink, the social fabric thins, the psychological reserves deplete. And what remains after every system has been calculated and every structure tested against the record of human history is a question so fundamental that it precedes every technical specification and survives every engineering solution. Can a human civilization be built to order and expected not to fail? Not a machine, not an ecosystem, not a government, a civilization. The full architecture of human collective existence, language, memory, purpose, trust, accumulated knowledge, social cooperation, shared identity, felt meaning, all of it sealed inside a container, launched into darkness, and asked to persist without interruption for longer than most of the civilizations that have ever existed on this planet. The Roman Empire is cited with regularity as the preeminent example of institutional longevity in Western history. It endured in its Western form for roughly 5 centuries, and in its Eastern continuation as the Byzantine Empire for nearly 15 centuries in total. But the Roman Empire that collapsed in 476 bore almost no resemblance to the republic that preceded it, which bore limited resemblance to the early monarchy, which bore little resemblance to the small agricultural settlement on the Tiber that tradition places in the 8th century before the Common Era. Roman civilization persisted not by remaining stable, but by transforming continuously and profoundly. It absorbed conquered peoples and their gods. It adopted new religions wholesale. It reformed its governance structures repeatedly, sometimes through orderly succession and sometimes through civil war. It expanded and contracted its territorial boundaries across centuries of military campaigning. It survived epidemics, famines, invasions, and periods of catastrophic internal fragmentation. And it reinvented itself fundamentally at least 3 or 4 times across its full lifespan. Each of these transformations was made possible by contact with the broader world, by the influx of new ideas arriving from Persia, from Egypt, from Greece, from the Germanic tribes pressing against its northern borders, by the absorption of new populations carrying new skills, new agricultural practices, new metallurgical knowledge, and new spiritual frameworks, by the economic pressure of competing empires that forced internal adaptation or imposed it through conquest, by the essential openness of a civilization embedded in a world full of other civilizations. A generation ship cannot transform in any of these ways. It cannot absorb new populations. It cannot import new ideas from neighboring cultures, because there are no neighboring cultures. It cannot expand its borders, because the hull is the border, and the hull does not grow. Its only available adaptive mechanism is internal reorganization, and internal reorganization in a materially closed system is always zero-sum. Every structural change that benefits one faction or generation necessarily disadvantages another. The political, social, and material flexibility that allowed terrestrial civilizations to survive and renew themselves across centuries is precisely what a sealed interstellar vessel cannot possess. This is not a limitation that more sophisticated engineering can overcome. It is a structural property of the concept itself. A generation ship is defined by its closure, sealed materially, sealed socially, sealed informationally. Nothing enters, nothing leaves. The system must generate all of its own stability from internal reserves alone, and internal reserves are finite by definition. Every conflict that is resolved consumes social capital that cannot be replenished from outside. Every material crisis that is overcome depletes physical resources that cannot be restocked. Every generation that maintains cohesion does so by drawing on cultural and institutional deposits that are being steadily diminished by the very act of sustaining the community through each successive difficulty. Think of it as an inheritance that can only be spent, never earned. The founding generation deposits into the ship's collective account social trust, shared purpose, technical expertise, institutional legitimacy, and the felt conviction that the mission is worth the sacrifice it demands. Each subsequent generation withdraws from that account to cover the costs of survival, the costs of conflict resolution, of crisis management, of maintaining discipline in the face of deprivation, of transmitting knowledge across the gap between one generation and the next. If the withdrawals are modest, and the deposits were substantial enough at the outset, the balance can persist for many generations, but the account earns no interest. It cannot be supplemented from any external source. Every crisis, every internal conflict, every failure of transmission, every episode of social fragmentation accelerates the rate of withdrawal. And the question is not whether the balance eventually reaches zero. Given sufficient time in a closed system, it must. The question is only whether it reaches zero before or after the ship reaches its destination. The answer depends on variables that cannot be reliably predicted before departure. How severe will the crises be? How effective will the conflict resolution mechanisms prove across generations that did not design them? How faithfully will critical knowledge be transmitted through educational systems that are themselves subject to the same drift, affecting every other institution aboard? How much social capital will each generation consume simply managing the psychological burden of permanent confinement? These questions involve the behavior of human beings across centuries, under conditions that have never previously existed, and they cannot be answered by computer simulation, by historical analogy, or by any amount of careful design. History offers specific cases that illuminate what happens to human communities placed under conditions approaching, though never fully replicating those of a generation ship. These cases do not prove that a generation ship would fail. Nothing in human experience can prove that with certainty, because nothing in human experience constitutes an adequate precedent, but they reveal with uncomfortable clarity what closed, isolated, resource-constrained communities tend to do when the pressures accumulate beyond what their institutional frameworks can absorb. The ancestral Puebloan civilization of the American Southwest constructed some of the most architecturally sophisticated settlements of the pre-Columbian world. Communities like those centered around Chaco Canyon maintained complex social hierarchies, extensive trade networks, and remarkable agricultural engineering across several centuries. Then, beginning in the late 13th century, something shifted. A combination of prolonged drought, systematic depletion of the surrounding forest resources that agricultural expansion had consumed, and what archaeological evidence suggests was escalating internal social conflict produced a collapse so complete that the great cliff dwellings were entirely abandoned within decades. The population dispersed. The institutional knowledge that had sustained the complex society did not transfer intact to the successor communities that eventually formed elsewhere. What had been a sophisticated civilization became, within a few generations, an archaeological mystery. The ancestral Puebloans had access to open air, natural water sources, biological ecosystems that could theoretically recover given sufficient time, and the physical freedom to relocate when conditions deteriorated beyond the point of recovery. They left. And even with all of these advantages, the civilization did not survive the compound pressure of resource depletion and social fracture. The Rapa Nui civilization of Easter Island presents an even starker illustration of what resource closure does to human communities over generational timescales. The Polynesian settlers who arrived on Easter Island, likely between 700 and 1100 CE, found a forested island of approximately 63 square miles. They built an extraordinary culture, erecting the famous Moai statues that required enormous, organized labor and sophisticated engineering. The population grew. Agricultural expansion accelerated. The forest was progressively cleared to support farming, to provide timber for canoe construction, and to supply the log rollers used to transport the massive stone figures. By approximately 1600, Easter Island had been essentially completely deforested. Without trees, topsoil eroded. Without topsoil, agricultural yields collapsed. Without canoes, deep-water fishing became impossible. The population crashed. Warfare became endemic. Cultural complexity dissolved. The society that had produced the Moai could no longer maintain the institutional framework required to erect them. When European explorers arrived in 1722, they encountered a population a fraction of its former size, living in conditions of deprivation and conflict that bore little resemblance to what the island's archaeology suggested had once existed. Easter Island was not a sealed system in the complete generation ship sense. The ocean surrounding it was always theoretically navigable, but the loss of the canoe-building knowledge, a direct consequence of deforestation, effectively sealed the island as surely as any hull plate. The population became trapped on a resource-depleted surface, with no practical means of departure and no external source of renewal. The Norse settlement of Greenland lasted roughly 4.5 centuries before failing entirely. Norse settlers, arriving around 985 CE under Eric the Red, established communities that maintained cattle farming, participated in the North Atlantic trade network, and built churches whose ruins survive to the present day. At their peak, the Greenlandic Norse settlements may have supported several thousand people. Then, across the 14th and 15th centuries, a combination of factors converged. The medieval warm period that had made Norse-style farming viable in Greenland's climate gave way to the cooling conditions of the Little Ice Age. Trade connections with Norway weakened as the Black Death devastated European populations and disrupted commerce. The Norse settlers, committed to a European farming culture that was becoming increasingly mismatched with the deteriorating climate, appear to have refused or been unable to adopt the hunting and seal-based subsistence strategies that allowed the Inuit people to survive in the same environment. The last written record of the Greenlandic Norse dates to 1408. When European ships arrived decades later, the settlements were empty. The final inhabitants had starved in a landscape they could no longer sustain themselves within. Surrounded by an ocean they no longer had the ships or the knowledge to effectively exploit. The Norse Greenland case is particularly instructive for the generation ship context, because it illustrates the danger of institutional rigidity in a changing environment. The Norse settlers possessed a coherent cultural identity, a functioning governance structure, and a shared framework of meaning derived from their European Christian heritage. These institutional strengths sustained them for centuries. But those same strengths, the cultural commitment to a specific way of life, the institutional resistance to adopting practices that conflicted with their identity as European farmers rather than Arctic hunters, prevented the adaptive flexibility that survival ultimately required. Their civilization was not destroyed by a sudden catastrophe. It was gradually suffocated by the gap between the institutional framework they had inherited and the environmental reality they actually inhabited. a generation ship would face an analogous dynamic. The institutional framework established at launch, the governance structures, the cultural practices, the educational systems, the social norms would be calibrated to the conditions and assumptions of the founding generation. As the voyage extends across generations and conditions slowly shift through the accumulation of all the processes already described, the gap between the inherited institutional framework and the actual lived reality aboard would gradually widen. The institutions designed at launch were optimized for launch conditions, not for conditions 2 centuries later. Adapting them requires the same institutional flexibility that the Norse settlers lacked, and it requires making that adaptation from within a community that has no external models to emulate, no neighboring civilization demonstrating alternative approaches, and no history of successful adaptation to draw from beyond whatever the ship's own record contains. Each of these historical cases involved populations with access to open air, natural water sources, functioning biological ecosystems, and the fundamental psychological grounding that comes from inhabiting a planet. Each nonetheless experienced severe cultural regression, critical knowledge loss, or complete civilizational collapse. A generation ship offers none of these environmental supports and demands institutional continuity across timescales that exceed every one of these historical examples. The radiation keeps falling through all of this. That fact deserves deliberate emphasis because it illustrates how the physical and human burdens interact and amplify each other across generational time. Galactic cosmic ray exposure does not pause because the community is navigating a governance crisis. DNA damage does not slow because the medical team has just lost a critical specialist to an industrial accident. Cancer rates do not plateau because the population is managing a food shortage that is consuming every available unit of institutional attention and labor. The radiation is constant, indifferent, cumulative. Each generation is biologically slightly more burdened than the one before it. Each successive cohort faces a marginally higher background rate of chronic illness, a marginally smaller pool of fully healthy working adults, a marginally greater demand on medical infrastructure that is itself degrading year by year. Over 5 or 10 generations, this cumulative biological erosion may remain individually manageable. Over 20 or 30 generations, it compounds into a systemic drag on the population's capacity to maintain the systems that keep them alive. More people are carrying chronic illness. More labor hours are absorbed by caregiving. Fewer skilled workers are available for the critical maintenance tasks that cannot be deferred. The genetic burden progressively reduces the effective working population below the raw number of people physically present aboard. A ship that departed with 20,000 people may, in generation 15, have only 14,000 healthy enough to work reliably. Of those, only a fraction will possess the highly specialized skills required for reactor maintenance, atmospheric chemistry calibration, or precision agricultural management. The population that the ship's designers calculated would be sufficient to sustain all critical functions was calculated for launch conditions, not for the biologically degraded population that actually exists 2 centuries into the voyage. This is the convergence point where every category of burden arrives simultaneously. The engineering systems degrade, the ecological margins narrow, the genetic health of the population declines, the social structures strain under accumulated pressure, the cultural memory that preserves critical institutional knowledge fades, the psychological resilience of individuals erodes. And each of these processes accelerates the others in ways that produce not linear decline, but cascading deterioration. Sicker people maintain systems less effectively. Poorly maintained systems produce environmental stresses that worsen health outcomes. Worsening health outcomes intensify social conflict over scarce medical resources. Social conflict disrupts the governance structures responsible for knowledge transmission and labor allocation. Disrupted knowledge transmission produces less effective maintenance in the generation that follows. Less effective maintenance accelerates the degradation of all physical systems simultaneously. The spiral tightens with each generation, while the resources available to arrest it diminish at exactly the same rate. No single one of these burdens is necessarily fatal in isolation. A well-designed ship might survive a period of serious social instability without losing critical technical capabilities. A robust population might endure a radiation-induced increase in cancer rates without the medical system collapsing entirely. A skilled engineering team might manage a cascade of simultaneous mechanical failures without losing the critical systems. But the generation ship does not face any of these challenges in isolation. It faces all of them simultaneously, continuously, and cumulatively for centuries, using a fixed and declining resource base operated by a population whose biological health, psychological resilience, and institutional coherence are all declining in parallel. The question is not whether any individual challenge can be overcome. The question is whether all of them can be overcome at the same time by the same population using the same finite resources across a timescale that exceeds every comparable achievement in the entire history of human civilization. Science fiction recognized the specific failure mode that emerges when this question is answered honestly, long before engineers and social scientists began confronting it systematically. Robert Heinlein's Orphans of the Sky, originally published as 2 novellas in 1941, depicted a generation ship whose later inhabitants have entirely forgotten that they are aboard a vessel. They believe the ship to be the whole of the universe. The concept of an outside, of a destination, of a mission, has been completely lost. The descendants of the original crew live as tribal communities within corridors they understand as simply the world, conducting rituals whose original engineering purposes they no longer comprehend, governed by a priesthood that enforces orthodoxy about the nature of their enclosed reality. Brian Aldiss explored the same territory in his 1958 novel Non-Stop, in which the ship's inhabitants have regressed to a semi-feral existence in an overgrown vessel they no longer understand as artificial. The metal walls have become for them simply the boundary of existence. The mission is not remembered, the destination is not imagined. The vessel continues traveling because its automated systems have not yet failed, not because anyone aboard understands where it is going or why. These narratives are not merely imaginative extrapolations. They are the logical endpoints of documented human behavioral patterns projected onto the generation ship timescale with the compounding effects of every pressure the ship generates. They describe not an unlikely worst case, but a statistically probable outcome, given what we actually know about knowledge transmission in isolated communities, about the psychology of inherited confinement, and about the institutional dynamics of organizations that lose contact with the external pressures that originally gave them purpose. The ancestral Puebloan builders, the Easter Islanders who raised the Moai, the Norse settlers of Greenland, none of these communities intended to fail. None of them made decisions that seemed at the time of making to be accelerating their own destruction. They made locally rational choices within the institutional and cultural frameworks they had inherited, responding to the immediate pressures visible to them without the capacity to observe the full arc of the long-term trajectory those choices were collectively tracing. A generation ship crew would face identical constraints. Each generation makes locally rational decisions within the framework they have inherited. Each generation responds to the immediate pressures visible to them in their own lifetimes. No generation has the capacity to observe the full trajectory their collective choices are tracing across centuries. The slow erosion of genetic health, the gradual narrowing of technical expertise, the incremental drift of institutional purpose, the barely perceptible thinning of cultural transmission, none of these processes are dramatic enough to demand urgent response in any single generation. Each looks manageable from within the generation experiencing it. The cumulative effect across 20 generations is visible only to an observer who can see the entire arc. There is no such observer aboard the ship. There is only the current generation doing what seems reasonable given what they can see, unaware of how much has already been lost and how much further the decline will extend before anyone recognizes it as irreversible. The ship does not fail the way dramatic narratives require. It does not explode. It does not collide with anything. It does not experience a single moment of catastrophic breakdown that retrospective analysis can identify as the point of no return. It fails the way all closed systems eventually fail, through entropy, through the slow, patient, invisible accumulation of losses too small to demand attention in isolation and too numerous to arrest in aggregate. The hull remains intact. The reactors continue producing power. The crops continue growing in their artificial light. The water continues flowing through its recycling systems. And inside this still functioning physical structure, the civilization that was supposed to operate, it has become something its founders would not recognize, something that may no longer know what it is, where it is going, or why the journey was ever undertaken. This scenario, a ship that functions mechanically while failing humanly, may be the most probable outcome of any generation ship attempt. Not because the engineering is impossible, the engineering is merely extraordinarily difficult, but because maintaining human civilization intact, purposeful, and technically competent across centuries of sealed confinement is a challenge of a categorically different order. It is the challenge that no blueprint addresses, no simulation captures, and no historical precedent suggests is within the demonstrated range of human institutional capability. The machine can be designed on paper. The civilization that must operate it cannot be designed at all. And civilization, it becomes increasingly clear as you examine every dimension of this problem, is the most fragile component the ship will ever carry. More fragile than the atmospheric recycling systems, more fragile than the reactor pressure vessels, more fragile than the bearing assemblies in the rotating habitat sections, more fragile than any physical structure that engineering skill can design and material science can manufacture. Because civilization is the one system aboard that cannot be repaired with fabricated replacement parts, cannot be restarted after a complete failure, cannot be maintained through recursive tooling chains that reach back to fundamental physical principles. It can only be transmitted, generation by generation, through the imperfect medium of human memory and human teaching and human example. And transmission, unlike manufacturing, has no quality control protocol, no dimensional tolerance specification, no verification procedure that can confirm the fidelity of what passes from one generation to the next. What passes is always something slightly different from what was sent, and over centuries, slightly different compounds into unrecognizable. This is the deepest challenge the generation ship concept forces us to confront. Not the distance, not the physics, not the engineering, the civilization. The question of whether human beings are capable of sustaining something as fragile and as essential as their own collective continuity across conditions that have been specifically designed by the nature of interstellar space itself to destroy it, and the answer that history, biology, psychology, and the logic of closed systems collectively suggest is not a comfortable one. And here is the thought that should stay with you long after this journey ends. The generation ship concept is not wild speculation. It is not the fantasy of science fiction writers disconnected from physical reality. It is not a fringe proposal existing at the margins of serious scientific inquiry. It is, by the assessment of physicists, engineers, and astrobiologists working within the constraints of established physical law, the most plausible method of interstellar human migration that the universe currently permits. Cryogenic suspension does not exist. Not almost. Not nearly. The fundamental biological feasibility of freezing a complete human organism and reviving it intact after decades or centuries has not been demonstrated at any scale. Relativistic travel is permitted by the equations but forbidden by any energy budget that bears contact with physical reality. Faster-than-light travel does not merely face engineering obstacles. It violates the foundational structure of space-time as understood by every experiment physics has ever conducted. Wormholes, warp drives, and quantum teleportation of biological matter remain either mathematically speculative or physically prohibited. If humans are ever to reach another star in physical form, carrying physical bodies across physical distance, and the generation ship or something so functionally equivalent to it that the distinction is cosmetic, is what the laws of this universe appear to require. The brutal reality is not that generation ships are one option among several, each with its own profile of advantages and drawbacks. The brutal reality is that generation ships may be the only option, and the only option may be functionally impossible. Not impossible, because the ship cannot be built. It probably can. Given sufficient resources, sufficient political will, and perhaps 2 or 3 more centuries of continued technological development, the material science challenges are formidable but not implausible. The propulsion requirements are enormous, but not categorically beyond what nuclear or fusion technology might eventually provide. The ecological engineering is daunting but builds on principles that are well understood, even if their execution at the required scale and duration remains entirely undemonstrated. The ship, in its physical sense, can probably be built. The civilization inside it probably cannot be sustained. This is the inversion that most people never anticipate. The part of the problem that looks hardest, the physics, the engineering, the energy requirements, the material science, is not actually the hardest part. It is merely the part that yields to technical solutions. Give engineers enough time and resources, and they will produce a hull that holds, reactors that sustain output, atmospheric systems that function, agricultural systems that feed the population. These are hard problems. They are not the hardest problem. The hardest problem is the people. The hardest problem is asking a human civilization to do something that no human civilization has ever done. To endure, sealed, isolated, confined, and purposeful, genuinely purposeful, not merely going through the institutional motions of purpose for longer than any nation, any empire, any religious tradition, or any cultural institution has ever persisted without transformation, disruption, or at least partial collapse. Without contact with the outside world, without the influx of new ideas, new populations, new resources, and new pressures that have historically been the engines of institutional renewal. Without the fundamental freedom that has always, in every terrestrial context, been the pressure valve through which civilizational stress eventually finds release, the freedom to leave. Remove that freedom, seal the container, launch it into darkness, and then ask what remains of human civilization after the door has been closed for 200 years. The question has never been answered, because the experiment has never been conducted, and the closest analogies available: island communities, isolated religious orders, extended polar expeditions, simulated Mars missions, all involve either much shorter durations, partial contact with the outside world, or both. None of them constitute adequate preparation for the specific combination of permanence, isolation, material closure, and multi-generational inheritance that defines the generation ship condition. Project Orion, studied seriously in the late 1950s, proposed riding the shockwaves of sequential nuclear detonations to velocities approaching a few % of light speed. The concept was abandoned after the Limited Test Ban Treaty of 1963 made atmospheric and space nuclear testing politically and legally untenable. Not because the physics was wrong, the physics worked. More recent proposals exist across the full spectrum of speculative ambition. Fusion drives that extract energy from the same process powering stars. Antimatter propulsion that converts mass directly to energy at efficiencies no chemical or nuclear reaction can approach. Laser-pushed light sails that use ground-based or orbital laser arrays to accelerate ultra-thin craft to significant fractions of light speed. Breakthrough Starshot, announced in 2016 with backing from Stephen Hawking and Yuri Milner, aims to use exactly this approach. An array of powerful lasers pushing gram-scale probes to approximately 20% of light speed, potentially reaching Proxima Centauri in roughly 20 years. But the probes in that proposal weigh a few grams. They carry no crew, they carry no life support. They carry no food, no water, no atmosphere, no medical facilities, no governance structures, no children, no elderly residents, no conflicts, no grief, no ambition, no resentment, and no need for meaning. Scaling from a gram-scale probe to a vessel capable of sustaining 20,000 people across centuries is not an engineering extrapolation. It is a categorical transformation of the problem. Every kilogram added to the payload multiplies the energy requirements. Every human being added to the manifest multiplies the life support complexity. Every generation added to the voyage multiplies every social, psychological, genetic, and institutional challenge by factors that do not scale linearly. The gram-scale probe is an elegant solution to the problem of reaching another star. It is not a solution to the problem of carrying humanity there. Consider what the first-generation ship proposal would actually require of the people who approved the launch. It would require assembling a founding population of somewhere between 20,000 and 40,000 individuals drawn from the full spectrum of human society, selected for genetic diversity, technical competence, psychological resilience, and interpersonal compatibility, and asking them to enter a vessel from which there is no return, toward a destination none of them will live to reach, on behalf of descendants whose consent cannot be obtained because those descendants do not yet exist. It would require designing a governance system capable of persisting for centuries without external legitimacy or the pressure valves that have historically made governance sustainable. It would require constructing educational institutions capable of transmitting not merely technical knowledge, but felt purpose across generations whose lived experience will become increasingly remote from the founding generation's frame of reference. It would require creating a culture robust enough to maintain institutional continuity across the full duration of the voyage, while remaining flexible enough to adapt to conditions that no pre-launch design can fully anticipate. And then it would require launching, knowing that once the engines ignite and the hull clears Earth's gravitational influence, every one of these requirements becomes the sole responsibility of the people inside. No external support, no course correction from outside, no second attempt if the civilization begins to fracture. The people who would approve such a launch would need to believe, with sufficient conviction to act on, that human nature is robust enough to sustain itself under conditions that human nature has never been tested against. That the social engineering embedded in the ship's design can achieve what no social system in the entirety of human experience has ever achieved. That the accumulated fragility of closed ecosystems, degrading machinery, cumulative radiation exposure, progressive genetic erosion, cultural drift across generations, and the psychological weight of permanent inherited confinement will not, across centuries, produce a failure cascade that transforms the vessel from an ark into a tomb. This is not pessimism. It is an honest assessment of what the historical, biological, psychological, and ecological evidence collectively indicates. The margin for success is narrower than most generation ship proposals publicly acknowledge. The consequences of failure are absolute and irreversible, and the experiment, if it is ever conducted, cannot be repeated. There is a particular cruelty embedded in the structure of the generation ship concept that becomes visible only when you hold all of its dimensions simultaneously in view. The cruelty is not that the mission is dangerous. Human beings have always pursued dangerous missions. The cruelty is not that the mission demands sacrifice. Every significant human achievement has demanded sacrifice of some kind. The cruelty is that the sacrifice demanded by the generation ship falls most heavily on the people who had the least say in whether the mission was undertaken at all. The founding generation chooses. Their decision is real, informed, and freely made. They understand what they are accepting. They believe in what they are attempting. The weight of their sacrifice is carried by a conviction that the mission justifies it. Whatever hardships they endure as volunteers. Their children did not volunteer. They were born into the mission the way people are born into poverty or into war, not as a consequence of their own choices, but as a consequence of the world their parents made. They can be given reasons to believe in the mission. They can be educated into its mythology and socialized into its institutional structures. But they cannot be given the founding generation's experience of choosing freely, of weighing alternatives, and selecting this path above all others, of feeling the departure as the fulfillment of a deeply held personal aspiration, rather than simply the only reality they have ever known. By the third or fourth generation, the distinction between a civilization and a captivity has become purely philosophical. The physical facts are identical. You are inside a sealed container. You cannot leave. The container is moving toward a destination you did not choose. The rules governing your life were established by people you never met. Your professional options are constrained by what the container requires of you, rather than by what you desire for yourself. Your reproductive choices may be shaped by what the population management system determines the container needs from you rather than by your own wishes. You will live your entire life inside this container, and you will die inside it. Whether that constitutes a civilization or a captivity depends entirely on whether you find the mission meaningful. And meaning, as every honest account of human psychology confirms, cannot be reliably manufactured by institutional design and transmitted intact across centuries to people whose lived experience has become progressively more remote from the experience that originally generated the meaning. The honest assessment, drawn from every discipline that bears on this question, converges on a conclusion that is neither comfortable nor dismissible. The generation ship concept represents the most physically plausible mechanism for interstellar human migration permitted by known physics. It demands no new science. It violates no established physical law. It requires only engineering at scales we have not yet achieved, and social sustainability across durations we have not yet demonstrated. On the first count, continued technological development offers at least the possibility of eventual adequacy. On the second count, the historical record offers no comparable example of success and several instructive examples of failure. The ship is not the hard part. The ship is merely the container. The container is a problem of physics and engineering, and physics and engineering, given sufficient time and resources, yield to determined human effort. The history of technology is a history of apparently impossible barriers crossed one by one as understanding deepened and capability expanded. There is no obvious reason in principle why the engineering challenges of a generation ship cannot eventually be resolved to a sufficient degree of reliability. The civilization inside the container is the hard part, and the civilization is a problem of human nature, of psychology, of sociology, of institutional dynamics, of cultural transmission across generations, of the felt experience of permanent inherited confinement and human nature, has never, in any context that constitutes a meaningful precedent, demonstrated the specific combination of resilience, flexibility, continuity, and sustained purposefulness that a generation ship would require. This asymmetry between the solvability of the engineering problem and the intractability of the human problem is the central truth about generation ships that most discussions of the concept either overlook or deliberately set aside. It is easier and more satisfying to design a hull than to answer the question of what fills the hull with meaning across 300 years. Hull design has a solution space that can be explored methodically. The question of how a sealed civilization maintains its coherence and purpose across centuries in the absence of every external support mechanism that has historically made civilization possible does not have a solution space in the same sense. It has a history, and the history is not encouraging. What the generation ship concept ultimately reveals, when examined with full honesty across all of its dimensions, is something profound about the nature of the challenge humanity faces in becoming an interstellar species. The challenge is not primarily technological. It never was. The distances are vast, and the engineering required to cross them is extraordinary. But engineering is the domain of problems that yield to systematic effort applied over sufficient time. The deeper challenge is existential. It is the challenge of carrying humanity, not merely human bodies, but human civilization in the full sense, with all its fragility and all its extraordinary capacity for both creation and self-destruction, across a void that is measured not only in distance but in time. Time is the medium through which everything human decays and transforms. Institutions lose their founding purpose. Languages drift beyond mutual comprehension. Knowledge narrows when the communities that held it become too small or too isolated to maintain the full breadth of what their predecessors understood. The felt conviction that a sacrifice is meaningful fades when the people making the sacrifice have no personal connection to the aspiration that originally justified it. None of these processes are failures of human intelligence or human will. They are properties of human existence in time, the same properties that make human civilization dynamic, adaptive, and creative under conditions of openness, and catastrophically fragile under conditions of closure. A generation ship is a machine for converting time into distance. It accepts that the journey requires more time than a single human life can span, and distributes the cost of that time across multiple generations, each carrying a portion of the burden toward a destination that only the last will see. The logic is impeccable. The physics supports it. The engineering in principle can accommodate it. What the logic, the physics, and the engineering cannot accommodate is the human reality of what it means to be one of the generations in the middle. Not the founding generation, whose sacrifice carries the weight of free choice and felt conviction. Not the arriving generation, whose sacrifice is redeemed by the sight of a new sun growing larger in whatever instruments they use to observe it. But the generations in between, the third generation, the seventh, the 12th, whose sacrifice carries neither the dignity of free choice nor the consolation of arrival, whose entire existence is spent in transit, in inheritance, in the middle of someone else's journey, with no exit and no horizon and no morning that brings anything genuinely new. These are the people the generation ship concept asks us to create. Not volunteers, not heroes. People born into a condition they did not choose, asked to maintain a purpose they did not originate, on behalf of descendants they will never meet, toward a world none of them will reach. Whether that is justifiable depends on questions that philosophy has not resolved and that the generation ship concept forces into a specificity and urgency that terrestrial ethics has never been required to confront. Whether it is survivable, whether the civilization those people are asked to carry can remain intact across the full duration of the crossing, depends on questions that history, biology, and psychology have answered consistently and across multiple lines of evidence, with something considerably short of confidence. The stars are not beyond reach because the distances are too great. The distances are vast, but they are traversable in principle. The stars are beyond reach because the bridge required to cross those distances is not made of metal or propellant or engineering brilliance. It is made of human continuity of memory carried forward without distortion, of purpose transmitted without dilution, of meaning sustained without the external reinforcement. That meaning has always, in every context humanity has ever inhabited, required to remain alive. Building that bridge is harder than building the ship. It may be harder than anything the human species has ever attempted. And the most unsettling aspect of the entire proposition is not the possibility of failure. It is the recognition that this may be the only bridge available. That if humanity is ever to become more than a single planet species in the physical sense, not merely sending instruments but sending people, not merely exploring but inhabiting then the generation ship, or something so close to it as to be indistinguishable is what the architecture of this universe appears to require. We do not yet know if we are the kind of species capable of building that bridge. We have never been tested at anything approaching the relevant scale. We have built civilizations that endured for centuries, but always in open worlds with horizons. We have sustained institutions across generations, but always with the renewal that contact with the broader world provides. We have demonstrated extraordinary resilience in the face of hardship, but always with the knowledge that the hardship was temporary, that the world outside continued, that the future was not yet fixed. The generation ship asks something different. It asks for resilience without the consolation of temporariness. It asks for purpose without the validation of external context. It asks for civilization without the openness that has always been civilization's most essential nutrient. Whether we can provide those things, whether human nature is capable of sustaining itself under conditions specifically designed to test every limit it possesses, is a question that will remain unanswered until the moment someone actually attempts the crossing. And the answer, when it finally comes, will be delivered not by engineers or physicists or social scientists, but by the people themselves, the people sealed inside the hull, the people born into the middle of the journey, the people who did not choose and cannot leave and must somehow, generation after generation, find enough reason in the inherited darkness to keep the lights on, keep the crops growing, keep the knowledge intact, keep the purpose alive. If they succeed, humanity will have demonstrated something genuinely extraordinary about its own nature, something that no terrestrial achievement has ever required us to demonstrate before. If they fail, the ship will continue traveling, the hull will hold, the reactors will sustain their output, the automated systems will maintain atmospheric chemistry within survivable parameters, and inside, in the corridors and the farms and the recycled air and the artificial light, something that was once a civilization will persist in whatever form 2 centuries of sealed confinement and all its accumulated pressures have left it, drifting between stars, carrying the memory of a world it can no longer reach, toward a world it may no longer understand how to inhabit. A candle that was lit in sunlight, burning now in a darkness deeper than the people who lit it ever fully imagined, tended by hands that do not remember the match. Whether that candle reaches the far shore still burning is the question the generation ship ultimately asks of us. Not of our engineering, not of our physics, not of our material science, or our propulsion technology, or our ecological design capability. Of us, of what we are, at the level that no blueprint reaches and no simulation captures, of whether the most fragile thing we have ever built, not the hull, not the reactor, not the atmospheric recyclers, but the civilization, the meaning, the continuity of human purpose across the silence of generations is strong enough to survive the crossing. We do not yet know the answer. We may not know it until someone opens the door on the other side and discovers what is still alive inside.